Well, first, thanks a lot for the kind introduction, and also thanks a lot for the invitation and for the organization of this amazing event. Indeed, so I was in Recon IIP in Tokyo actually until about 1 year ago, and then I moved to Singapore to ESSEC Business School, which is actually based in France. So I just want to say a word about that actually. We have now 2 campuses, one in Paris, in a suburb of Paris actually, with a lot of people you might want to connect to actually. So if you want to, to chat with them, if you visit France someday or whatever, we have many people working on Bayesian statistics and on high dimensional statistics. In Singapore, there are less people, actually, 2, and one of them is me. So that's much smaller, but a new campus. If you ever come to Singapore, you can also come and say hello. I'd like to thank Professor Ben David for the previous talk. Actually, I really enjoyed. I know your book, obviously. I worked on it a lot to prepare my own lectures. So it was really nice to see this talk. But still, there's one thing I would like to say. I would like to make actually a little statement in defense of pigeons. I felt I had to do it because I really like them. Actually, this is a photo I took myself a few weeks ago in Singapore. It's a colored pigeon, which actually you can probably also see in Okinawa. I know they're in Japan, actually. They're called aobato, which in Japanese, if I understand well, means blue pigeon. And as you can see, they're green. So that's mystery. But anyway, I have a strong bias. I like these birds, and I really think that even though some of them are prone to superstition, many of them like actually rational thinking and science and debate, actually. So I just wanted to say that. Just practical information. Indeed, like this user-friendly introduction to PAC-Bayes bond was published recently, but it's been on the web for some time. So you can find the version on archive that matches like 95%. It contains 95% of the published version, and also the slides. So I sent a link to the slides on Slack. But if you did not see it, then you can find them actually on my webpage. Okay, so this lecture will be about actually statistical learning theory, but subtopic actually of statistical learning theory. So another family of generalization bounds than Vapnik type bounds, actually. So this is actually a survey of what I will do in the 2 lectures, actually. So the part 1 is today's lecture, and part 2 is for tomorrow. So I will start by yet another introduction to generalization bounds, actually, but it will just like be the opportunity to introduce my notations, which are matches like 75%, the one of the previous talk, but there are some discrepancies. I will explain what a PAC-Bayes bound is, and I don't want to oversell these tools, but what I want to do today is to explain the difference, actually, what you can get and what you cannot get if you compare them actually to Vapnik bounds and to worst case bounds, actually. And then I will take some time to explain you how to minimize these bounds, and then I will end up with, if I have time, a survey of like many kinds of bounds of PAC-Bayes bounds you can find in the literature. Okay, so I start with notations immediately. Okay, but so I will use the following notation. So I will essentially focus on classification and regression problems. I will still use generic notation, so you will have objects. Okay, X that would be essentially vectors, or well, I think of images or whatever, but essentially vectors, and labels that would be, of course, either discrete for classification or continuous for regression. And my notation for classifiers will be like that. Okay, so f theta, a classifier, is a function from X object space to Y, the label space, and it's indexed by some parameter theta. So I know that if you think in terms of neural networks, like in this image, for example, you would probably usually use the notation W maybe for the weights. So I come from statistics, so my bias is for the notation or for the parameter actually theta. Okay, so here you have an example. Maybe, for example, you would use vectors to encode images as inputs. So the picture on the left would be your X. This would be your f theta, and the thetas would be the weights that you have in the arrows in your neural network. And then the output must give an accurate prediction of the name of the species of the animal. Okay, so my notation for the loss function will be L, which is quite similar, I think, to the previous talk. And I will also focus on the generalization risk as an expectation. Okay, so take just the loss function. And you average the loss function when the object and label are drawn from some probability distribution P. That's essentially the objective and the thing that we're trying to minimize in this talk, okay? So essentially, my ultimate objective will be the smallest possible generalization error in the class of predictors that we choose. And for example, like previous talk, in the realizable case, this would be 0. In some case, it would be non-zero. We still target the ultimate objective, that is this infimum on the predictor set. Okay, and obviously, if you think in terms of images, you don't know what would be the probability distribution of the images you will have to classify in the future. On the other hand, you have samples. So one convenient assumption is that your sample is IID from the same distribution than the images you will have to classify in the future. So I will make this simplifying assumption for now, and obviously, like most of the theory relies on it. I will mention in the end maybe like some works where people try to relax on this. But for now, we assume that the data is IID from the probability distribution that you use in the definition of the risk, actually. So then when you have data, you can obviously, that's obviously the empirical mean corresponding to this expectation here, and that's the empirical risk or empirical error. So here again, the definition matches the previous talk, even though the notation is a little different. So I use this Rn actually for the empirical risk. I will motivate the theory by a small example, even though like from the previous talk, you already have good motivation for the theory, but still I prepared a very toy example just to visualize something that would be useful for the rest of the lecture actually. So I just sampled data, X, very actually standard and very easy example. So X is uniform on the unit interval. You cannot imagine a simpler domain for the object. And Y is, well, a function that's not completely linear of X plus some noise. So the data looks like that. And obviously, if I give this to you or to my students, like as an exam question, you know that you would, well, probably not use linear regression, but you have like many non-linear regression tools you could use to estimate such a regression function. You could use support vector regression if you don't have a prior on the shape of the function or whatever, any kind of non-parametric regression. I just want to illustrate something with the simplest, actually, statistical method ever, that is regular histograms. So by histograms, and using the quadratic loss here. So by histograms, I just mean function that would be constant on a small interval. So I cut the unit interval in k bins, and in each of these bins, I want my function to be constant. Okay. So as I'm super good in Python, I was able to code the histogram myself, that's what I got actually here. So looks reasonable. It captures kind of the V shape. It's not super smooth. Obviously, I made the choice of the histogram. If I wanted something smooth, I should have chosen something else. But anyway, this is what I have with k bins. And question is, how did I choose the number of bins? And you know that obviously it matters a lot when it comes to the generalization error. For example, if you take only one bin, then actually the function you obtain is just the average of the whole data set, of the whole Ys actually. On the other hand, if you take too many bins, like 100, then in some bins, you only have one data point actually, so you tend to almost interpolate. And if you take 200 or 300, you will completely interpolate the data actually. So obviously, you still have the kind of V shape as a trend, but you have too much noise around it. You obviously know that, but then I tried that for all possible number of bins from 0 to 50, which is enough to illustrate here what I wanted to show you. And then you can see actually that if you compare the test error to the, that would correspond to the R of theta actually, to the empirical risk, that is the Rn of theta, then they seem to match for a small case actually, and then at some point they diverge. Okay, they're not similar. So obviously the test, the empirical risk will decrease because I told you like if you take a huge number in the end of bins, you will interpolate the data perfectly, so you will reach a 0 empirical risk. But more importantly, what I'm interested in here is the fact that at some point the distance between the empirical risk and the test risk becomes large. And it might sound counterintuitive, right? I don't come from computer science, I come from statistics, probability. So I know the law of large number, and I know that if I fix a parameter theta, then when the sample size grows, the empirical risk will be close to the true risk. So of course, I could expect here that the orange and the blue lines should actually be close to one to the other. Because for one fixed parameter, then actually the orange one is supposed, like the blue one is supposed to be an unbiased estimator of the blue one. The point is, of course, when you're doing statistical learning, you don't have actually a parameter that is fixed. You learn a parameter from the data, and then it breaks the assumptions, right, of the law of large numbers. Sense that if in the empirical risk here you plug a theta hat that depends on the data. By the way, I will always use this notation S for summary, like the short notation of the whole sample xi, yi, I from 1 to n. Okay. So then you see that all the terms actually in the empirical risk, L of yi f theta hat of xi, they all depend on the whole data. So they're no longer independent. So actually you don't have anymore the law of large numbers. So then question is, can we quantify a distance between the two, between actually the true risk of a theta hat that depends on the data and the empirical error? And the answer is yes, because you attended the previous lecture, and you know that, for example, using Vapnik-Charbonenky type bounds, or okay, finer version with Rademacher complexity, etc., you can give upper bound on this difference. And actually, you mentioned it in your talk, but there are many approaches, variants actually, to try to prove generalization bounds and to control the difference of the two risks for learned parameters. Some of them, for example, relying on the notion of algorithmic stability. And what I'm going to discuss more details today actually is approaches that are all more or less the same with small variants that are related on information theory and Bayesian point of view. So either minimum description length, information bounds, PAC-Bayes, etc. All of this is connected. And I'll try to give you today some insights of what is different in these bounds with respect to Vapnik bounds. So to clarify, actually, what I'm going to do today is to cover empirical bounds. That is actually bounds that will provide you a generalization bound, but the generalization bound is numerical, actually, something that you can compute on the data. So essentially, we'll have the knowledge that the risk of a classifier is smaller than something that you can actually compute on the data, and that hopefully can be smaller than one sometimes. Tomorrow, I will focus more on the theoretical aspects and on the rates of convergence, in the sense like checking if your generalization error would ultimately, when the sample size grows, match the best one in the set of classifiers you have. I want to apologize first. Actually, I will do today and tomorrow, I will spend like 95% of the lecture assuming that the loss is bounded between 0 and 1, which includes, you know, the 0-1 error for classification. But if you want to do regression, yeah, it imposes strong, you know, restrictions. So I will discuss today, but probably more tomorrow, actually, papers where this assumption is relaxed. It's feasible. You cannot obviously have zero assumption. You need assumption, but you can relax some of them. The point is, it adds a little complexity to the bound. So I prefer to present the simple version with more assumptions today and then discuss extensions later, rather than to start with a bound that would be a little too complex. So anyway, here is a statement of Vapnik bound. So I'm not going to talk too much about it. Actually, I just wanted to remind it. Anyway, like if you have a set of classifiers, f theta, you know the Vapnik dimension of this set of classifiers. Then actually, with large probability for any parameter that you learn on the data, you will have a control of the generalization error by the empirical error plus a term which is in square root of the dimension over n, Vapnik dimension over n, okay, up to log terms. And then you have the log of 1 over delta, just the tail bound for the probability, actually. So you choose your probability confidence level like 95%, and then this term becomes a constant. Okay, so I just wanted to remind you that. And now I will move to PAC-Bayes bound, but just before actually I state the first PAC-Bayes bound, I just want to explain a major difference, which will turn out to be both convenient and inconvenient, depends on the situation, actually. Just that statistics, we have a definition of estimator, which is a measurable function of the data. Well, I mean, don't know if you ever had the opportunity to build a non-measurable estimator, but anyway, we should, like something that obviously is not in the definition and should be there is that it should be an algorithm. So you should have something that would actually be able to compute your theta s. But anyway, what happens is that you simply have a map from the data space to the parameter space. Input, you give data. Output, you get a parameter. And it's not what we have with PAC-Bayes, actually. So what we have with PAC-Bayes, and it will make notations a little heavier, but we have, in some sense, two steps, actually. You know, what we will estimate from the data is not a parameter, but a probability distribution on the parameter set. So I use this notation, M of theta. I mean, it's a recurring notation for today and tomorrow. It's the set of probability measures on theta. And essentially, we will map the sample, okay, to a probability distribution on the parameter space. And then, okay, if you want to imagine a practical scenario where you use this bound, a practical procedure that would correspond to it, for example, would be to sample a parameter from this probability distribution. So, few remarks about that. It's supposed to include the first case as a special case. Of course, if your probability distribution is just a point mass on a single estimator, in theory, it includes the first definition as a special case. It's not really the way we will see it in PAC-Bayes bound. It's not always, actually, sometimes we cannot really study this kind of point estimator with PAC-Bayes bounds. Also, it seems like there is a reason why there is a word Bayes in PAC-Bayes bounds. It seems inspired by Bayesian statistics. And indeed, if you know Bayesian statistics, you know that in Bayesian statistics, you choose a prior, which would be the case also in PAC-Bayes bound. And then you do all the statistical inference through the posterior, and the posterior is the distribution of the parameter given the sample, actually. So it's a probability distribution that depends on the sample. It matches this definition. The point is that I want to insist on the fact that with PAC-Bayes bound, even though it was in some sense designed with a kind of analogy to the Bayesian statistics framework, we're not going to focus on this kind of randomized estimators. I will show you various kinds of randomized estimators, but they cannot always be interpreted as actually Bayesian in the, you know, hardcore Bayesian school sense. Okay. Still, actually, the PAC-Bayes bound will provide you some generalization bound on practical procedure related to this kind of randomized procedures. So the idea would be as follows, actually. Stricto sensu, the most classical PAC-Bayes bound that will give you information on this procedure. First, you learn a probability distribution on your sample. And then each time you have a new object, you will also draw a new parameter theta from your posterior distribution, from your randomized estimator, okay? And then you use it for prediction. And each time you have a new data point, you would use a new sampling independent from your rho hat, actually, here. Then just through the law of large number, this, if you take the empirical mean of this thing, it will converge to the expectation. So expectation over both things, first over the data sample from P, which corresponds actually to the definition of our generalization risk. But you have also expectation under the parameter, and this one I will keep, okay? So the object we'll study for now is this. So it looks a little heavier, and sometimes people write R of rho instead of this expectation to shorten the notation. But maybe it's because I have a taste for ugliness, or maybe it's, I don't know. I want to keep safe. In order to remember that it's an expectation under a posterior, I will always keep this, even if it's heavier. Sorry, it might make the formulas heavier, but I think it's good to remember that it's an expectation under the randomized estimator. Okay, that's enough preparation. So now I can state a PAC-Bayes bound, and probably many things are not clear in it. So actually, what I will do is that I really took a lot of time. Actually, I will take half an hour to. You know, I take this bound, I throw it to you quite raw, but we will, you know, chew it together for like each term for 20, 30 minutes, so that we can understand what is similar and what is different to Vapnik's bound in this. So first, McAllister's PAC-Bayes bound, so it's the first PAC-Bayes bound that was published. I will give the actually reference of the paper later. So as I said, actually, there is still an analogy with Bayesian statistics. We fix a prior, and then you observe data. What happens is that with large probability on the data, you are in a situation where whatever the probability distribution row on the parameter space you choose, even if it's dependent on the data, okay, then actually you can connect its generalization error to its empirical error, plus still, like in Vapnik bound, a term in square root of blah blah over n, okay? The second term in the blah blah is actually still a log of something over delta, so it's still like related to the tail of the distribution, okay, and to the tail event here. Now, you have, instead of the Vapnik dimension, you have this KL rho pi, which actually is notation for the Kullback-Leibler divergence, which I will explain, actually. I will define, I will remind the definition and provide an explanation in the next slides. The only thing I want to insist on here, because I think it's not always clear with the standard notation of the topic, actually. Very often people in the statement of the bound, they don't put a hat on the row. Still, actually, in this bound, like, the row is actually allowed to depend on the data. So it matches the definition of randomized estimation procedure I proposed before. So if you have a randomized estimation procedure like the Bayesian posterior, or I will define actually many later, then you can just use this bound to study it, okay? Then what I will explain a little later is that we have quite good procedures to minimize this bound, and that this will be a way actually to define randomized classification procedures. That will be in the second time. So first time, actually, I want to comment a little on the KL divergence. Yes?
Here it's a bound on the expectation, where the VC bounds are a bound on the probability of being on the tail of the expectation. So this doesn't take the variance into account. It only tells you what the expectation is, but not how likely you are to be away from the expectation.
Exactly. So I will comment on this actually also, in the sense that this was the original bound, and you have many variants where actually people would, for example, provide bound on aggregation procedure, actually, or also on sometimes trying to control the, actually, I did not include it in the slide. It's mentioned in the book. It's not in the slide. Like control the variance, actually, so the difference between the mean value and what you will have with. So there are variants. I will discuss some of them. For now, I'll just focus on this, even though I will really try to connect it to once again to practical bounds a little later. For now, I want to discuss a little the complexity term, in the sense that in the Vapnik's bound, you have this, okay, this D here that measures the complexity, the richness actually of your set of classifiers. I want to explain here why, intuitively at least, why the KL here plays a similar role. First, I want to remind the definition actually. So Kullback-Leibler divergence between rho and pi. In the discrete case, say, to start with a simple formula, it's provided by this definition here. So it's the sum of the rho of theta, the probability of theta on the rho, times the log of rho of theta over pi of theta, which might actually seems not well defined in some context. You don't have to worry if rho is equal to 0. Just take the convention, like the limit, you know, the continuity. So rho 0 log 0 is 0. But problem might be if you have rho positive over pi, which will be 0. In this case, you have to take infinity, which actually will anyway be something we will avoid, of course, when we use the bounds, but we have a definition, okay, in this case, we take infinity if pi is 0 and rho is non-zero. That would be for the discrete case. If you are in a real case with actually continuous random variables, you could have a formula with integral, etc. And if you just want general formula, you could define it in terms of expectation. So if rho has a density with respect to pi, okay, then you can just take the expectation of log of d rho over d pi under rho. And you see that actually this general definition matches the previous one in the sense that if rho is actually, if rho and pi are discrete actually, then the expectation under rho is the sum of rho of theta times what you have inside the expectation. So it matches actually the definition. You have an interpretation of this in terms of information theory and code length, etc. These are things I might comment later tomorrow, connections with information bounds. But for now, I want more to relate it actually to the complexity term in generalization bound. Just first one remark, have this that will be useful in one or two proofs, that the KL between rho and pi is non-negative, and actually it can be equal to 0, but only in the case where rho is equal to pi. So it's not a distance, it's not symmetric actually, but it has some similarities with the distance, like you can call it, I don't know, quasi-distance or whatever. This aspect is highlighted a lot actually in some papers on PAC-Bayes, but I really think that the most important is what I will discuss in like from the next slides. So I just want to give you intuition, and in order to give you intuition on this, I'm going to build priors and posteriors that might be too simple to use in practice, but if you apply the bound on this prior and this posterior, maybe you start to get a hint on what can be done with this bound actually. So I will start with this situation. So B is the set in red, and A is the set inside the black line. Okay, so I just made it, colored it white inside for readability, but it's everything that's inside, okay? And I decided to use as a prior the uniform distribution on A, and as a posterior, the uniform distribution on B, okay? So uniform distribution, okay, like assume of course that A and B have, you know, are non-empty interiors, etc., etc. So you can, but anyway, we have this. So the density of pi is the, so sorry, I use the like abusive notation that we have often in Bayesian statistics, where actually we substitute sometimes like from the probability to its density. So actually its density function is the indicator of theta being in A, actually, sorry, over V of A, which is the volume of A, okay? Same for rho. Now, what happens if you want to compute the KL between rho and pi? Of course, I should not ask questions because I already uploaded the slides on Slack. But if you do it here in this case, you see that the problem is that rho gives mass to a part of B that is outside the set A. And so what it means is that actually you don't have a density. D rho over d pi is not defined in this case. So according to the definition, in this case, the KL is infinite. So you could use the PAC-Bayes bound in this case. It will be completely true, but it will tell you that the prediction risk is smaller than infinity, and it doesn't give a lot of information. We can improve things a little, actually. If I take B within A, okay, then actually the density of rho with respect to pi is defined actually as the ratio of these two, of the density of rho and the density of pi. And it's just actually the volume of A over the volume of B times the indicator that theta is in B. Okay, so this formula is valid for all theta in A, but anyway, I will only focus on this because when I compute the KL between rho and pi, I will take actually the expectation under rho. So the expectation under the uniform distribution on the small set, okay? So when I do this, actually, what will happen is that this indicator, if theta is drawn from rho, theta is in B, so the indicator here is always equal to 1, actually. So it means that, sorry, the ratio of the densities is simply the log of the volume of A over the volume of B, and then we have here an explicit formula. So it seems to look like something simpler. Okay. Now I will apply this to a very specific setting. Assume that your parameter space is a Euclidean ball, centered at 0. Say you don't have a prior on what is the region of the space to be. So you just take a Euclidean ball, centered at 0, with a big radius C. And then I'm going to take, for rho, say a uniform ball, a distribution on the ball, but this time a Euclidean ball with a much smaller radius and centered around some parameter theta naught of interest. We have a formula for the volume of a ball. I cannot remember it by heart, so I copied it from Wikipedia. I hope it's correct. What matters here is that, okay, you have many, many constants, pi to the d, gamma function, d over 2 plus 1, but it doesn't really matter because d, of course, is the same for the prior and the parameter, is the dimension of the parameter space. So the only thing that changes is the radius, okay? And you see that essentially it depends in the radius in r to the d. So I could have applied just the previous formula, okay? In this case, the KL between prior and posterior would be the log of the volume of the parameter set over the log of the small ball around theta naught, okay? And if I do so, then I have the log of C to the D over R to the D, which is actually D times the log of C over epsilon. And then you see something magic, which is that actually it's not so different. Okay, we had Vapnik dimension in Vapnik bounds, and in the PAC-Bayes bound, we had the KL, but if you choose some specific prior and posterior, the dimension of the parameter space, okay, in this time it's not Vapnik dimension, it's the actual dimension in terms of vector space, but it's there, okay? It's hidden in there, and many choices we will do will make this dimension appear actually in the bound. So I would say this is a similarity actually between the two bounds, and you see here how the complexity of the parameter set have an influence on learning. So just to recap, I promise that we will choose the bound many times together until things are clear. We want to control the generalization error of a randomized procedure. Then we have it's controlled by its empirical risk, but also plus square root of complexity term. Not super explicit, okay, it's in terms of KL divergence. Well, actually, if I'm in a setting where my parameter space is a Euclidean ball with a radius C, and for example, I have my empirical risk minimizer, I compute my empirical risk minimizer, then what I can do is to take as a posterior a ball with very small radius centered around the empirical risk minimizer. So it's not like exactly the ERM, but rho then in this case is just like random perturbation of the ERM. And it makes actually things compatible with PAC-Bayes bound. And in this case, your generalization error is like that. It becomes square root of D times log of C over epsilon instead of the KL. Make sense? Or I mean, if something is not clear, maybe I can take questions because otherwise, what follows might be a little boring. Okay, so then let's assume it's clear. So this highlights, in some sense, not to get too lost, similarity between PAC-Bayes and between Vapnik type bound. Now I want to highlight also something different. And the something different here is that in my row here, I still have a degree of freedom. I could choose epsilon as I want. Okay, and obviously there will be a balance that I will explicit later, actually, because if epsilon is very small, and the limit, if epsilon becomes 0, then actually the empirical term here will become exactly the risk of the empirical risk minimizer. Otherwise, it can be slightly larger. But on the other hand, if epsilon is large, I might actually kill the log term here. Okay, and that's something important. I will illustrate this on a simplest classification problem ever, but just to get a sense of a major difference and something that we will actually use in more complex examples later. So this example, the xi's are distributed, not uniformly. They might have any distribution actually between -1 and 1. And the classifiers are just a cut. On the left, it has to be 0. On the right, it has to be red. So it's really an easy classification problem, okay? But we just have to decide where to cut. And to make things even simpler, I assume that the classification problem is realizable in the sense that there is a theta star that gives the perfect answer. So I just want to find where it is. So typically, the data would look like that, okay? On the left, you have negative examples. On the right, you have positive examples. And you want to learn where to cut so that you classify well future instances. Obviously, I'm not saying I'm doing something super deep here, by the way. I'm just trying to illustrate something. If you're doing ERM, okay, empirical risk minimization, of course, it's not uniquely defined. I don't see a problem here. You can take any theta at somewhere in between A. So A will be like the largest of the blue points and be the smallest of the red points. You can take any theta at here, actually. Okay, makes sense? Any theta between A and B will have an empirical error equal to 0. And essentially, what you get from Vapnik type bound, obviously I did not use the best bound I could here because it's a realizable scenario actually, so I could remove the square root, but we'll discuss this later actually. Well, I just take a basic application of the bound I stated before, and the Vapnik dimension in this case is 1 actually, so you just have that the generalization error would be in like logs over 1 over square root n. Okay? You don't have the empirical risk anymore, it's equal to 0. Now, what I want to show you is that with the PAC-Bayes bound, you could use exactly the previous result, okay? So take, for example, pi uniform on -1, 1. And you can take rho at whatever you want, actually. But here, I would propose actually to use the uniform distribution on AB. Why? Because any theta between A and B gives, 0 empirical risk. So if I sample rho theta from this row, I will have a 0 prediction error. On the other hand, remember actually the previous result. Remember we are in a special case, but our balls are in dimension 1 now, so they're just segments, okay? Remember the C over epsilon. If you can take epsilon larger, then you make the bond smaller, actually. So here, something nice is that my C over epsilon simply becomes 2 over B minus A. And then you can see that actually the bound is not always the same. It's really dependent on the data set you see. And depending on the distribution of X, if this distribution is nice enough and all the blue points are close to -1 and all the red points are close to +1, then you can take a big posterior, very almost equal to the prior. And in this case, you will have actually a much smaller bond. On the other hand, if the interval is very narrow, then it's less favorable. And actually, at some point, the log could become much larger, and this might become a problem, actually. So to illustrate this, just compare these two data sets, okay? They might be drawn from the same probability distribution, or it might be that actually in the second case, the scenario is much easier. The xi's are actually quite apart. There is a gap in the middle where you cannot have any data points. But you can choose any ERM. Vapnik's bound will always give you a result which is like constant in this problem, okay? And the PAC-Bayes bound, well, see, this time the B minus A would be much larger and the complexity term becomes smaller. So what I hoped to make intuitive with this example is that yes, the complexity term in KL bounds will depend on the dimension, but on the other hand, it will also be related to the easiness of the problem. And actually, we'll see later that you might kill some dimension if the posterior can be very flat in some directions, actually. So just to illustrate the empirical risk in this case, you see, like I assume I have a bigger data set, but with the same problem. See, the empirical risk is like a stairs, it decreases, then it's constant on some part, and then it increases. And okay, it's a very simplified thing, but in the end, what we saw is that it's related to how big is the area where the minimum is flat, where the risk is flat, actually. So here you have a flat minimum, and if it can be quite big, actually, then the bound will become better. So just empirical for now, no statement, but it seems intuitively that if you have a flat minimum somewhere, then the PAC-Bayes bound could give you a better numerical generalization bound. Okay?
Well, how will it look if the sample does not separate so nicely the blue from the red?
I have examples later, actually. But essentially, you can always, not always, you have assumptions, but you have good understanding on assumptions where you could relate actually the performance of the PAC-Bayes procedure to the performance of the ERM. And sometimes you can improve the bound if actually you still have flatness of the minimum in some directions, for example. So it will work too, actually. So I have less simplified examples and statements later. Okay, I want to discuss another topic actually first. It's a minimization of the bound. And I just want to discuss this still with this McAllister bound. So I want to discuss two strategies. Maybe the first one is not a strategy actually, or at least not for a complex model, but it's more something theoretical that gives good insight and that allows to connect with other approaches. You could minimize this bond numerically, and I will discuss that later. But for now, I want to try to understand what the exact minimizer look like. And we don't have an explicit formula, but if I change the bound just a little, we will actually. So just allow me to use this simple trick, okay, to there is obviously a big mistake in this. I will fix the slides, that's shameful. But anyway, you don't have the square root of on A and B in the right-hand side, but just use this very simple inequality. So simple that I am not able to copy and paste it properly, but anyway. So then actually you can rewrite McAllister's bound in this way. So the square root, not really a simplification, maybe a complication. Actually, I introduce an additional parameter, lambda, But then for some time, I will not try to optimize with respect to lambda, and instead I will just think of the bound for a fixed lambda. So that's another equivalent way to state Macalister's bound, okay? It appears that we can minimize the right-hand side here with respect to rho explicitly. And then we can later minimize to lambda, okay? But if we want to do it, actually, it turns out that it matches a procedure that was studied before, actually, in statistics. That's depending on where you read paper, like it can be called Gibbs posterior, Gibbs estimator, exponentially weighted aggregation. You have many, many names, actually, but essentially, so it's a probability distribution, randomized estimation procedure. It depends on pi, it depends on lambda, so I will denote it by pi hat of lambda from now. And it's defined as, it has a density with respect to pi, and the density is proportional to E times exponential of minus the lambda times the empirical risk. Of course, it has to be a probability distribution. Its expectation, like the integral should be equal to 1. So in order to renormalize, I have to divide by the expectation. Well, anyway, that's the definition of what I will call Gibbs posterior. And then actually we have this theorem that tells you that it's the exact minimizer of the right-hand side. I wanted to mention this for many reasons. First, similarity between PAC-Bayes and Bayes. In Bayesian statistics, if you know Bayesian statistics, you start with the prior, and the posterior you get it by using Bayes formula, which is multiplying the prior by the likelihood. Here, if E to the minus lambda times R is a likelihood, then you would get a posterior in the Bayesian sense. It appears that if the empirical risk, the loss you use inside is actually the minus log likelihood, and if you take lambda equal to n to compensate for the 1 over n in front of R, then you get exactly the standard Bayesian posterior. So it's within this definition. You know, it's not likely that if you check the bound above, it's not likely that lambda equal to n is a good choice, because the n over 8n will give you 1 over 8, so it gives a bound that is of order 1, which is not a super good idea. Might be in other settings, but for now it's not a good idea. Anyway, the standard Bayes posterior is included within this setting. The point is that this actually equality was known in Bayesian statistics. In some sense, the minimization of this bound corresponds to maximization of the elbow in Bayesian statistics, and it's something used for variational approximations. People knew that if you maximize the minus this function, which they call the elbow, you actually recover the posterior. Now, how comes that this is actually the minimizer? I'm a little slow, so I should. I will just still comment on the proof quickly, actually. So the idea of the proof is just that you compute directly the KL between any row, okay, a variable, and then the pi hat, the Gibbs posterior. And because you have explicit formula for the density of pi hat, actually, which is given here, when you take the log of its density with respect to pi, you have log of exponential of minus lambda at the risk, but log of exponential is the identity. And this time I make no mistake, so I'm happy. But then actually, you end up with the expectation of the log of 0 over d pi, plus lambda times the empirical risk, and plus a term, which, okay, it's the log of the normalizing constant, but it's also not dependent on rho, actually, it's a constant. So then it means that if you write that the expectation of the sum is the sum of the expectation, you end up with the KL between rho and pi, lambda times the risk of the rho, actually, and then a constant. But look at the very first term in the derivations, is the KL between rho and pi. We know it's non-negative, and we know it will be 0 only if rho is equal to pi. So it tells you that the last, because everything after that is equalities, the last line will be minimized when rho is equal to a pi hat, okay? So you have the minimizer, and moreover, as you know that if you take rho equal to pi hat, everything becomes an equality, you know that the last line is equal to 0, and it tells you what is actually the value of the bound. So in some sense, we could write the less explicit statement, but if you take actually the Gibbs posterior, you have minimized the PAC-Bayes bound, and then you have this formula for the risk. And then you can optimize in lambda, good luck with this. And then you would have minimized exactly your bound. The thing is that when people were working with simple models, like, okay, dimension is regression in dimension 3, 4, 10, okay, even a few hundreds, you can actually sample from pi lambda using all the computational tools that were developed in Bayesian statistics, so MCMC, extra. So from that time, I have papers where we did not care at all about optimization method. We just focused on, like using standard MCMC techniques, and we were able to have like nice results on slightly complex model, but of course not neural networks, not deep neural networks. Yeah, not so easy to optimize in lambda. I want to discuss different approach, approximate minimization of the bound, but which makes things so simpler, actually, so faster that this is sometimes the only hope when you have very complex models. And I want to discuss this because, well, first, it will lead to a few nice applications. Also, like it has very nice connection still with Bayesian statistics, in the sense that it's an idea, actually, that came from Bayesian community. Say that, okay, remember this program here, like optimization program, we try to minimize the PAC-Bayes bound. So, okay, I removed in the theorem, I removed the term that do not depend on rho, and I just took like the simplest part. You minimize this with respect to rho. Point is, in Bayesian statistics, sometimes people knew that to sample from this rho or from this pi, sorry, pi hat, it's a little tricky. So they proposed to do approximate minimization. That is to minimize only on the subset of the set of all probability distribution. And that's essentially what they called variational inference. You could do the same here, actually. You could decide to minimize, okay, to minimize the bound, but where rho is constrained to be in a smaller set F that is more tractable, like say the set of all Gaussians. So that's what I'm going to do. So now instead of finding the exact minimizer of the bound, which might be a crazy probability distribution that I might not be able to deal with, I'm just going to say, okay, let's take a Gaussian. And then it's easier because I only have to estimate the mean and variance. So the second term, by the way, in this case is explicit, KL between two. So of course, if you take a posterior, that's Gaussian. The prior, it's also convenient to take it Gaussian. In this case, you have an explicit formula, which again is a little cumbersome, but it's still something in the end quite helpful. By the way, just check, okay, if you take rho equal to pi, then the difference between mu1 and mu0, so the quadratic term in mu here becomes 0. If then sigma 0 and sigma 1 will be also equal, so their determinants are equal, so the log of the ratio is log of 1, so it's 0. And then the trace of sigma 1, sigma 0 inverse, well, if sigma 0 is equal to sigma 1, then it's the trace of the identity, which in dimension d is actually d, so minus d becomes 0. So what I said is true, okay, like this, if the two are equal, these remain equal to 0. But there is more to say here. I would just want to illustrate again this flat minimum thing, just in order to connect with the application that comes in a few minutes. So let's come back to dimension 1 once again, because I was not able to draw pictures with larger dimensions. So you have, say, two Gaussians, rho and pi. Okay, pi in blue and rho in red. In this case, the formula where the determinants of 1-by-1 matrix and the trace of a 1-by-1 matrix, you can simplify, okay, it becomes the numbers themselves. So the KL becomes simpler. And then you can see two things. Obviously, first thing is related to this term here, mu0 and mu1, actually. If rho starts to move quite far away from the center of pi, actually, to infinity, then this term will blow to infinity. So first, the bound will not be super informative if your prior does not give enough mass to points that are relevant for classification. But more importantly, to connect with the previous toy example, what happens if you take a rho that is thinner and thinner, okay? So compare with the general here, I have rho that is quite flat, and then diet for rho, and it becomes thinner. So the variance term has to go to 0. In this case, look at the bound here. If the variance term sigma 1 goes to 0, you will also have that the KL will blow to infinity, actually. So that's something you have to avoid. You can still relate that, and sorry, I'm still not doing like formal statement. This will be more tomorrow, actually, but for now, I'm still giving like kind of intuitive things. But essentially, if your risk looks like that, which is bad luck, but that, say, maybe it could happen, then actually the ERM actually has a small empirical risk here. And you have a rho here that is, still charging the support of like regions where pi gives some weight. You can center it around theta hat. But if you want essentially that the PAC-Bayes bound remains close to Vapnik bound, you would need to have a very, very small variance so that any theta sampled from this Gaussian here would have a risk close to the empirical risk. And in some sense here, the minimum is so narrow that if you want to do so, you have to take sigma 1 almost equal to 0. And it's not good. In this case, it will make the PAC-Bayes bond large. Yes, you can see this? Okay, now just assume that the minimum is, well, yes? Okay, but the point is, at some point, if it's really too narrow, it means that the prior has to know in advance where the parameter is. So obviously, you could improve things by improving the prior. And by the way, we're going to play with optimizing priors tomorrow also. But for now, with a given prior, at some point, you cannot make a row, you cannot make the variance too small. Otherwise, you will make the bound become too large. On the other hand, same prior. If you have a flat minimum, here again, like you can relax, rho can just spread a little, and you can still have, like expectation on the rho that will remain close to the empirical risk. But okay, for sigma 1, do not have to be super, super small, and then the bound will be less problematic. Now, actually, what made this approximation popular is that you can like using Gaussians here, for example, or any parameterized family instead of the Gibbs posterior. That's a little less easy to deal with. Then actually, it's that to minimize the bound, you just want to minimize in the end with respect to mu1 and sigma 1. So it's just a minimization with no longer with respect to a probability distribution, but just with like a vector and a matrix here. So you can use essentially any optimization tools you like. And again, what makes it convenient in this case is that as the criterion you want to minimize is an expectation, obviously you can guess that there is some stochastic optimization procedure that will work quite well with this kind of criterion actually. So if, to make things tractable, it's easier actually to reparameterize the problem. And instead of using the variance matrix, you take its square root, okay, in the sense that you replace sigma 1 by u times u transpose. Sigma 1 is symmetric, so it can always be written in this way. And then you just want to minimize, okay, with respect to mu1 and u, this bound, okay? So this term is an expectation with respect to this Gaussian here. And this term, well, it's the formula that I wrote in the slides before and that I didn't want to copy and paste here because it would be a little ugly, but we have an explicit formula essentially, so that's not a problem. If you don't have an explicit formula for the expectation in the left term here, then just can reparameterize here, okay? If you sample a psi from a centered Gaussian distribution and with variance identity, okay? And then you take mu1 plus u psi, it's distributed according to a Gaussian centered at mu1 and with variance u times u transpose. So in the end, you manage to replace here the expectation with respect to the posterior by the expectation with respect to a fixed distribution, a Gaussian. And then obviously, if you don't have a closed formula for this, you can just replace the expectation by sampling from psi, write your stochastic gradient algorithm, and then run it on the data and hope that things will work. I did not discuss convergence of the algorithm here. It appears that actually it can be studied quite nicely in the sense that it was proven in various papers actually that the good properties that you have in the risk in terms of optimization, you will recover them also in the expectation. What I mean is that, for example, if the risk function is convex, in theta, which makes like the optimization problem obviously much easier. Then actually the minimization problem in the first line of this slide in mu and u is also convex. If it's smooth, the risk, then actually the expectation is also a smooth function of mu and u. So essentially, if you can prove that your stochastic gradient algorithm converges, then you also can prove for minimization of the empirical risk, you can also prove that it will converge to the minimization of the bound above. So it's not obviously if you use it for more complex non-convex problems where you don't know if the SGD converges, you have the same problem here, but it's that's life. Okay, you have to deal with it. And I just want to end up this part on minimizing bound with an application which is not mine at all, actually. That's not really what I'm working on, but I really wanted to mention it because it's been a motivation to study PAC-Bayes bond recently, actually. It really echoed the previous talk because you mentioned at some point that if you train a neural network, usually the Vapnik type bound will not give you something informative. Here, disclaimer, I did not really run an experiment. I just made up the number. But if you learn through Vapnik bound that your empirical risk is smaller than 30 something, in the case of classification, you don't really care about that, okay? Because obviously the classification risk is a probability. It should be between 0 and 1. So if you know that it's smaller than something that is larger than 1, you don't get any information. I think that everybody thought that most generalization bound would not be able to give any reliable information on neural network. But actually, it's not the case. And there were papers, and actually, I think like the really striking papers using PAC-Bayes was this paper by Carolina Tsugaite and Dan Roy, which is quite beautiful. I will essentially give their result and comment a little, but I mean, they both wrote quite beautiful theoretical papers on PAC-Bayes with various co-authors and students. But this paper is more practical. It's something quite beautiful. I really like the discussion in this paper because very often when we derive theory, we say, okay, I'm going to prove something, but accept this, don't criticize this assumption. Okay, it's a little tricky to optimize this, but okay, assume we can do it. I will discuss that later, and I will not. But here, I really think that they took PAC-Bayes bound, and they really took all the parts that people don't discuss usually, and really came up with clever ideas, actually, to make them functional on neural networks. Well, and it's striking that almost no one used this idea before, for example. The red line is the landscape, the risk landscape of your neural network when the parameter is in dimension 1. I don't know if it means anything for a neural network, but okay. You have many minima, and you know, like you're dealing, for example, with images. It's feasible to find the perfect classifier on the set, on the data set, actually. So you might have many minima, and that would be exactly equal to 0. The point is that some of them are close to the center of the prior, some of them are not. How do you choose your prior? Well, it is quite simple, actually. They just said, okay, you never initialize your SGD as 0. It's quite a bad idea. You initialize it at a random starting point. Why don't I take a prior centered at this starting point? Because here, obviously, I hope that the algorithm will converge to a minimizer that will close to the initialization, and that it will still have mass under the prior. And in most papers with simpler models, people were just taking pi centered at 0, as I did before, actually. That's something that numerically helps, actually, with the bound, which makes sense, and which is not prohibited by theory, by the way. So far, the bound I gave you, the PAC-Bayes bound I gave you, pi is not allowed to depend on the data, even though there are data dependent prior bounds, actually. But the one I gave you, the pi has to be fixed in the sense that it has to be independent from the data. But there is no problem with randomizing the prior in the same way that you randomize the starting point of the SGD. Yeah, so they had a few tricks like that. Some of them are classical, like obviously to replace the 0-1 error by a convex surrogate. That's not. But some of them were more dedicated to PAC-Bayes bound. So for example, we know how to choose the initialization now. We don't know how to choose the variance of the prior. And essentially, they optimized with respect to the variance, but in a way that is allowed by theory, which is more or less equivalent actually to taking a mixture of Gaussian. So instead of taking exactly a Gaussian as a prior, they allowed many Gaussian with various scales. And in some sense, at some point, the bound will focus on the results given by the most adequate prior. And they got that. And just, okay, it's a lot of numbers. I just want to comment a few of them. Well, anyway, just take like, so they use it on neural network, not like the biggest possible, but still like they use it on a nice data set. And they train various architectures and they computed the PAC-Bayes bound. And there's something quite, yes, okay. Nice in the sense that if you see the PAC-Bayes bound here, they have, okay, compared to test error 0.01, 1% error on the test set, PAC-Bayes bound is 0.16. Well, it's not extremely tight, I would admit, but it's smaller than 0.5. So it still tells you something, at least we learned something today, is that neural networks do a little better than pure randomness, okay? So it was quite a surprise in the sense that, okay, if you count the number of parameters here in the neural network, so it's about 500,000. Vapnik, I don't know if bound on the Vapnik dimension is quite accurate, but it's a little complicated actually. But they found papers where people computed actually the Vapnik dimension of this neural network, and the best estimate they had was 26 million. So obviously, square root of 26 million times log n over n, you really need a large n to make this small. On the other hand, look at the KL divergence. I told you in the beginning, there is a dimension hidden in the KL divergence, but on the other hand, you can kill some dimension if your minima is flat, if your minimum is flat in some direction. See, the KL bound is 5,000. Compared to the number of parameters, it means that actually the PAC-Bayes bound take advantage of the fact that there is an intrinsic dimension actually of the data set. Some direction matters less than others, etc. And when you optimize properly the covariance matrix of the posterior, okay, it's not enough to be tight, but it's enough to be non-vacuous, which I think already at that time was a surprise. It does not give, by the way, any theoretical explanation on why neural networks work, okay? Because it just tells you on the data you have, the PAC-Bayes bound tells you that you have at least, at most 15% error rate. It does not tell you that on future data you will have the same phenomenon. So it's like something purely empirical, but it's still a valid numerical certificate. And it's in a few, like it's the NIST data set actually. So it's like a few 10,000 something. Like, yeah. So like the relation between the PAC-Bayes bounds and the rate of convergence is something I will comment a little more actually tomorrow. So like this one is purely empirical. I'm saying like everything related to rates will come tomorrow. I just wanted to show this example because I find it quite striking. It's motivated, to be honest, like 2016 was a bad time for people working on PAC-Bayes. We are running out of job. And then after this paper, poof, many people working on it again. So that was quite cool. But I wanted to cite some of the recent papers on it. It's the opportunity to mention like some of the prolific authors group on this topic. They have like two things about the paper that came later. If you compare to Dugaitai and Roy. So they also bring new tricks to make the bond tighter and tighter. And this is really nice contribution. On the other hand, sometimes they report bonds that I believe are a little optimistic in the sense that they also do sample splitting for this. And in the end, even though they are able to improve on Dugaitai and Roy's paper, the fact that they have PAC-Bayes bond like that are 0.02 in the end is over optimistic, and you will not get that if you don't do sample splitting actually. So just be careful to this. But like really, there are super nice ideas on algorithm to tune properly, like to use to minimize properly PAC-Bayes bonds, etc. Okay, so that's more or less everything for today. I just have a few slides. I call that a zoo of PAC-Bayes bonds because you understood probably from the previous slides that I like animals, especially pigeons. And I just want to, okay, it's not a complete overview, but I just want to mention a few things about this generalization bound. And once again, like the excess bound rate of convergence will be tomorrow. But on the generalization bound, so that's actually the original paper of Mike Allister from Colt 98, I think, where I took the bound that I cited before. I lied a little in the sense that the bound in this paper has slightly worse constants. It was improved later by other authors. To improve constants, even if you divide the bound by, 1.5 or something, in terms of the application I showed before, might mean a lot actually. So there were many attempts to make the bound tighter and tighter. Okay, when we were doing logistic regression with it 20 years ago, you didn't really care to divide the bound by 1.5, but in this case, if you divide the bound by 1.5, then the generalization bound will move from 0.15 to 0.1. So it's a big improvement actually. Now, of course, most of the literature is not about that. There are bounds, I mentioned that, and I will discuss this a little more tomorrow, like bound that will try to get rid of the, like boundedness, IID assumption, etc. Also, something equally important, I think, is bounds that because they take slightly different form, they might be easier to optimize with gradient or stochastic gradient algorithm. That's also something important, of course. One that is very convenient, and maybe it's not so apparent in this talk actually, because I did not give proofs, but Catoni worked a lot on PAC-Bayes bound actually from 2000 about, and he stated many results, but what's super nice with this paper, actually, where this result is taken from, is that it's the most Lego-style proof you will find ever, in the sense that you have bricks, you plug the bricks into each other, and then if you want to change any assumption on the bound, you just remove the brick, put another one, and everything else works fine. So for example, it has this bound, which now would not seem maybe so interesting because it really looks like McAllister's bound once you actually split the square root into two terms with the lambda trick, okay? The only different thing is that you don't have the square root n in the log, actually, so there is a slight improvement here. But one of the nice things is that in this bound, for example, just by changing the last line of the proof, and instead of using Markov inequality and the Chernoff trick, you just use Jensen inequality at some point, and then you end up with a bound. People call it de-randomized, which is not a proper name maybe, because actually it's actually still random. It's more like de-expected, it should be called. So what is here? What's this bound? You still fix lambda and pi the prior, and you decide in advance a randomized estimator rho hat. For example, you decide the Gibbs posterior that comes by minimizing the first bound here. And then you get your data, you compute your randomized procedure, rho hat, on the data, and you sample once a parameter theta from it. And then even if you don't sample medium, you just sample once, you still have the same guarantee in the sense that this time the probability 1 minus delta is not only on the data, it's on the data plus on your drawing of the parameter. And you have that, in this case, you have a point parameter for which the true risk is smaller than the empirical risk plus, and this is the d-expected version of the KL, so the log of the ratio d rho hat over d pi, actually. So in some sense, it tells you that a bound that minimizes the PAC-Bayes bound with the expectation term here is the optimal posterior, in some sense, is tight enough, concentrated enough in a given region of the space, so that if you sample from it instead of taking the expectation, you still have good bounds, actually. So there is a story, actually, about the preprint where these bounds are taken from, because actually it's not published, but then Olivier Catoni has 2 books about this topic. So actually, the first one is from Saint-Flour Probability Summer School. So it's a summer school a little like this one, but on probability theory. And sometimes when they feel, like open-minded for more applied topics, they would invite statisticians too. That's crazy. Anyway, so they invited Olivier to give a lecture on stochastic optimization, statistical learning theory in general. That was 2001, and he got like also at some point he just wrote McAllister's paper, and he talked also a little about PAC-Bayes bounds. And then later he wrote this preprint actually as a kind of extension of the content of the lecture notes. That's actually exactly at the time where I met him, because he was my PhD advisor actually. And I met him just when he submitted this paper to Annals of Statistics. It was about 70 pages long. And then I did my PhD, and after like two years, maybe and a half or something, I asked him like, what happened with this paper? And he told me, they told me it's too long, but it took them 1 year and a half to send me the reviews. And meanwhile, I wrote 70 more pages, so I don't know what to do. And then the editor of Annals of Stats, actually, so it's the IMS, Institute of Mathematical Statistics, say, okay, like, let's stop about that and let's just print it as a little book, actually. So that's the story beyond this book. The point is, so just not so in the sense that book contains many tight bounds, super nice application. It explains how to connect, especially PAC-Bayes bound to support vector machine, to information bounds, etc. But then the simplest bounds stated here, actually, they are not anymore in the book. For some reason, they are written in a little more cryptic version. So it's still nice to read these preprints that I don't even know if you can find it on the web, but anyway. Like other group of authors, there was a paper actually by Seeger that was super nice in 2002. So essentially, he derived an alternative version of McAllister's bound. But if you stop the proof before the end, you get actually an even tighter bound. That was not completely explicit, but then it's been rewritten by various group of authors, Andreas Maurer, and then there were a few more papers. Probably the more readable version is in a very nice paper also by Tolstikin and Seldin, actually. So also Evgeny Seldin has a very prolific group actually on the PAC-Bayes bound that wrote many super cool papers. I state their version of the bound, even though the same phenomenon was already in Seeger's bound, and it's something that you discussed also like in your class. Like in the realizable case, we know that the bound should be tighter. And essentially, they have this version, which obviously is related like to different concentration inequalities they use in the proof. You see that the complexity term over n here, you don't have the square root, and here it is with the square root, but it is multiplied by the expectation of the risk. Tells you what? That, okay, if the risk is bad, if the risk is close to 1, if it's a difficult classification problem, this term is dominant, and it will be the more or less the usual PAC-Bayes bound plus an additional term here. But if the problem is realizable, and sometimes a little more than realizable, to be honest, because it has to be realizable for a row that has a non-zero KL with respect to pi. So maybe, like not for a point mass, but for example, for a uniform distribution on a very small ball, but not zero radius. And then in this case, if you can find actually, I did not write something here, if this is equal to 0, actually, so in the realizable case, sorry, it's the first time I use this set of slides actually, so there might be a few typos. I apologize for that, but I will fix this actually and upload it on, so you can download the fixed version after the talk. So anyway, in this case, the square root term cancels, actually vanishes, and then you just have the term in 1 over n, so faster rate. So actually, when I discussed the intuitive example in the beginning, here you see that theta drawn from the posterior that was uniform on AB has a 0 empirical error, and thus actually I should have used this bound instead. So you will have this. Still, it depends on B minus A, but it's not in 1 over square root n, it's in 1 over n. Okay. Something else that I did not actually discuss more, but it echoes your question like from 1 hour ago. These are bounds in expectation with respect to the posterior. Yeah, okay. I said sometimes you can just draw a single parameter from the posterior and stop there, and you will also have generalization bound. But in some sense, it's not something maybe we like to do. It seems a little not robust maybe to the randomization in your draw or something. Ensemble methods are popular, right? And if you draw many times for the posterior and you make the many predictors you get vote, it's an ensemble. So PAC-Bayes bound should give you guarantees on ensemble, but it's not the case in the original bound actually. So there were many attempts to fix things, and for example, this nice paper by Pascal Germain and many co-authors from Canada actually, so another group yet. The PhD advisor was François Laviolette actually, and there were also like another prolific group on PAC-Bayes. They have a series of papers on this. They call that a weighted majority vote. So you sample a few times for the Bayesian posterior, or many times, and then you make the prediction vote, and you take you predict the label that receives the majority vote. Do you still have guarantee? Yes, but you have to adapt the bound just a little actually. So you have to work. I just wanted to mention this paper in case you want to read proofs. Actually, it might be the most, like a posteriori, one of the most accessible proofs of the PAC-Bayes bound, also by the same group. So this paper actually is mostly about numerical aspects of PAC-Bayes. Actually, they try to optimize for linear classifiers. That was before people switched to neural networks with PAC-Bayes. But also, they state a version of a PAC-Bayes bound, which, well, a little abstract, but it can be used as a lemma from which you can derive all the bounds I gave before in the slides before. And the proof is quite short, actually, so it's something nice. Also, the proof contains some terms about the exponential moments of the probability distribution, of the loss, sorry, etc. And so you can see where the boundedness assumption comes from, but you also have hints on what to do if you want to remove these assumptions. So for this reason, I recommend this paper. And I just want to take the opportunity, because you have two papers from this group from Quebec, actually, under the direction of François Laviolette, to remember him, because unfortunately, like about 2 years ago, actually in December 2021, he was sick and passed away. So that's actually a very sad loss for the community. Okay, well, I just added, in case you think I talk too much and this is too long, reference to other tutorials actually that appeared from us. There was one by the founder of the theory, McAllister. It's like a 10 pages document on arXiv, very easy to read and very insightful. Also by Tim Van Herven, about at the same time, introduction. And more recently, like a survey by Benjamin Gage that covers all the recent literatures, also on the computational aspects, etc. So that's very informative in terms of references. So that's it for today. Tomorrow we'll cover the other topic, the mutual information and rates of convergence, etc. So it will be a little less intuitions, but a little more of the theory side. And then if you have questions, I'm happy to try to answer them.
Today's next speaker is Pierre Alquier about PAC-Bayes. Pierre, are you ready? Yeah. Okay, so please start.
Okay, so thank you. Welcome back. So today I will cover, I promised yesterday, more theoretical side of PAC-Bayes bonds about rates of convergence. I will try to do it slowly, actually. So I will cover 3 different topics, and they are not really completely independent, but at least a little. So maybe I can take breaks between each of the 3 topics, and we can have questions in the middle of the talk. We'll see. Anyway, what I want to do first is to show you that the PAC. So yesterday I showed you empirical PAC-Bayes bond. You can minimize them on data, and then you get, the kind of numerical certificate on how good your prediction will be in the future. But you can also slightly switch to different point of view and just twist a little the proof to get a slightly different kind of PAC-Bayes bonds, which will be about the excess risk. That is, if your sample size grows, is large enough, will you get at some point close to the optimal prediction with your set of predictors? And that's also an important question, of course. So that will be the topic of the first part, excess risk bond. How to do it, how to use the tools I presented yesterday to get this kind of rates of convergence. General ones in the first time. In the second time, I will explain, and it's a little beyond PAC-Bayes actually. It's something that would work for any kind of PAC learning, but including PAC-Bayes. So what kind of assumptions would lead to faster rates? And the last topic, I think, is very important, and there are many publications in these information bounds recently. So I want to explain the connection with PAC-Bayes bonds, which actually turns out to be how to optimize not the posterior but the prior. Okay, yesterday I told you, if you have a prior, then you have data, then you can optimize the bond to get a posterior. But actually, in theory, once you have a posterior, there is an optimal prior that would minimize the PAC-Bayes bond. And this gives you immediately the what is called mutual information bound. Sometimes it makes the bound a little tighter, sometimes very much tighter, actually. So that's worth thinking about it. Before I start, and now that everyone is back from the coffee break, I have a kind of embarrassing question, sorry. But this morning I woke up, I was super happy to teach my second class, and then I got an email by a reviewer from Gold saying, oh, this paper is not in my area of expertise, I want to drop it. So I'm looking for an emergency reviewer. So of course it's anonymous, so don't say yes now. And of course you will, the best strategy is not to say yes. But if you want to, you can say the private message on Slack. And then I can, do whatever you want. I can write a piece of paper saying that you're my friend for life or whatever. So if it's not really about PAC-Bayes, it's a little about, still a little Bayesian learning and Bayes theory. But if you know a little on the topic, please save my life. So, okay, now I'll start with the, that's for real. I mean, that's not a joke. So if you're interested, really, please. Just to recap on yesterday's notation. So the sample S, so objects Xi's, labels Yi, sometimes IID, sometimes not, but in this talk, IID for now. And at the very end, actually, I will give a few references to on PAC-Bayes bond without the IID assumptions. The risk, which is the expected loss under the data distribution, okay? And the oracle risk, so it's the object of interest today, okay? Can we get a procedure whose risk will be actually ultimately for large sample size R star, the oracle risk. And then the empirical risk, so the empirical mean corresponding to the prediction risk. And so yesterday we focused on these kind of generalized estimators, so procedures that would map the data set to a probability distribution okay, on the parameter, on the weight space. And then once you have this probability distribution, okay, for me, what's important is that you can compute a bound. And in practice, what's important is that you can also get prediction by sampling parameters from the probability distribution rho hat. Okay, so today the objective is actually, if you use some of the randomized estimation procedures I introduced yesterday, would their prediction risk like be close in some sense to the true optimal oracle risk? And at some point yesterday, when I listed many bounds that appeared in the past 20 years, I mentioned Catoni's PAC-Bayes bound. This one is a little similar actually to the previous McAllister's bound, but I told you Catoni's proof is nice because you can actually change parts of it to get kind of different results without changing the global shape of the proof actually. And for example, I mentioned this result that if you fix a randomized estimator, but like the first bound, of course, motivates, for example, the Gibbs estimator, which was the minimizer of the bound. But if you decide in advance that you're going to use it, and if you're annoyed by the expectation in the bound, and if you're annoyed by having to sample many times from it, you can just actually sample just once. And you have the promise, thanks to the second version of Catoni's bound, that actually, even if you sample only once from the Gibbs posterior, then you would still have like empirical risk that, the prediction risk that will be close to the empirical risk plus the expected version of the bound. It turns out that in Catoni's proof, if you change a little some piece of it again, you will get what in this paper is called a PAC-Bayes bound in expectation. But actually, at that time, there were similar work by authors in statistics and information theory, like Tong Zhang's paper, where they derived exactly similar results, and they called them information bounds. And actually, the link between information and PAC-Bayes, I will discuss it a little in detail later. But for now, just see the difference between the previous bound. The previous bound had this blah, blah, blah with probability at least mod minus delta. So large probability, of course, you take delta quite small. Now we don't have a probability anymore. We just have a comparison between the left-hand side and the right-hand side in expectation. It's a little less informative, of course, because you might have the same like expectation that are close, but still on some event it might be very different. Everything I will say, actually, I will derive from this inequality could be derived also from high probability bounds. They are just a little more complicated. So I preferred, for the sake of simplicity, for the sake of approximate simplicity, to state things in expectation. I will explain why. Actually, I will derive a few things from this inequality, but my first objective is to explain why you can use this inequality and everything we did yesterday, actually, to get some guarantees on actually a comparison to the real risk here, the R star, okay, the oracle. So that's today's objective, right? For now, in Catoni's bound, you still have the empirical risk on the right-hand side. Oh, yes, by the way, that's, okay. There's a recent paper by Grunwald. I will cite actually some of the works by Grunwald later, but I actually call that kind of inequality PAC-Bayes, so that's kind of cute. It's no longer probably approximately correct because there is no probability, but it's expectation, so it's a mean. So it's a mean approximately correct. That's PAC-Bayes. That's a cute name. Anyway, last reminder. Remember this minimizer of the first PAC-Bayes bound, the PAC-Bayes bound in large probability, actually. So you have this, you want to find once the prior pi is fixed, you want to minimize the expectation under a randomized estimator plus the KL between this randomized estimator and the prior. And actually, we proved together yesterday that the solution is given by this Gibbs estimator, Gibbs posterior, exponentially weighted aggregate, etc. And it turns out that for some calibration of lambda and for some choice of loss function, this will actually also turn out to be the posterior in a Bayesian sense. But more generally, we consider this object as an optimizer, minimizer of the right-hand side. So just a few steps, and really elementary things. So each line is a little heavy, but the whole is just very easy manipulations. If I decide to use Catonese bound in expectation to the Gibbs to apply it to the Gibbs posterior. What's nice is that the right-hand side, okay, the right-hand side in the first line here of the three equations, the first line, the right-hand side is actually exactly minimized by this choice of pi at, okay? This is what we proved, and this is what the first line in the block reminds you, okay? So then it means that what you have inside of the expectation is actually the infimum of this quantity. Okay, so pi at reaches the infimum with respect to rho in the second line actually. So first line inside the expectation you have an infimum, and okay, it's lucky. Expectation of an infimum is smaller than the infimum of the expectation. So I can switch the two infimum and expectations, okay? And then when you have that, things become quite nice because actually, look here. The infimum in rho is outside the expectation. So it means that the rho will no longer depend on the data. Okay, in some sense, that's why the expectation of the infimum is smaller than the infimum of the expectation. When the infimum is within the expectation, it can depend on the data you integrate you respect with. If you take it out of the expectation, it's no longer dependent on the data. So actually, it's infimum on, in some sense, it's conceptually it's infimum on a smaller set of probability distribution. So because of this, the rho does not longer depend on the data. So you integrate Rn of theta both with respect to the sample and to respect to the parameter, but you remember or not your first class in measure theory or in integration, like integrate when you have a function of two variables, you can integrate with the first one and with the second one, or with the second one and then the first one, doesn't matter. This is a Fubini-Tonelli theorem actually, okay? So in this case, you can actually integrate first in rho and then in S, but the expectation of the empirical risk in S is actually the true risk, the real risk here. So actually another way to rewrite the oracle bound is this. And in this version, actually, it's explicit now that you have the real risk and no longer the empirical risk on the right-hand side. So in some sense, what I managed to do is to transform a practical tool into a non-practical one. Big success. But obviously I have an idea in mind, is that now what is on the right-hand side is no longer data dependent. It only depends on, you know, probability distribution on the data, on the prior, etc. So I can maybe upper bound things by data independent terms and thus get a rate of convergence actually. So that's what we will do. I must say that this bound actually, for me it's curious. So in PAC learning, if you open any book about Vapnik type bound, you have empirical bounds and then you have oracle type bounds, excess risk bounds like that. For some reason in PAC-Bayes theory, people really focused on the empirical bounds. And I got a huge number of papers rejected because people told me like, okay, the right-hand side does not depend on the data, so it's not a good bound. Like, yeah, okay, actually, I don't know if you noticed, but I did it on purpose. So, well, that's life. Different people have different objectives. This one, of course, once again, it's not the first step. The first step was really probability bound from which you can derive optimal, like the minimizer of the right-hand side, and it's not if you don't exactly minimize. Remember yesterday, you can do things approximately, minimize on fusible distributions, like Gaussian distributions. You can use algorithm to minimize these bounds, so it's a very practical object. Then actually, it turns out that the same bound, just with a slight modification, can also be used to understand the theoretical property now of the estimator that we derived from the first bound. So that's really two steps. There's really an order. And this one now is the one you need for theory. So just be careful, actually. I was able to derive these results because here, remember the first line of the three-line derivation, I told you like what you have inside the expectation is an infimum. So it's dependent on the choice I made here to use the pi at. I use the Gibbs, it's the minimizer of the right-hand side, and then I can do everything. So this result will not work for any randomized estimator. Actually, it turns out that by being a little careful, you can also derive similar results for approximate minimizers, like variational approximations, etc. I decided not to include this in the slide, but essentially, here, the left-hand side is constrained. I choose now a good randomized estimator motivated by yesterday. And then for this one, I know that it generalizes as well as what the right-hand side tells you. And in the right-hand side, you have an infimum of a rho. So I don't have to take rho equal to what I have in the left-hand side. I also got the paper rejected for this, right? So trying to explain. Left-hand side is the estimator we use in practice. It's the one motivated by the theory yesterday. It is the one you compute with your algorithm. Right-hand side, it's anything you want, as long as you get an upper bound of the right-hand side that will be small enough, okay? So we can make choices. So anything you want in the right-hand side, anything clever enough to get a tight bound, okay? So to illustrate this, I wanted to reuse first the same examples than yesterday, because at least like that's something now we are used to. So if the prior, the simple case where your prior is a Euclidean ball, say center at 0 for now, radius C, and then the uniform, like the posterior, just to match yesterday's example, just to use computations that we already did together, okay? I'm going to take a uniform distribution on the ball centered around a theta star of interest. Actually, in this case, a good idea is to take the theta star if there is one that will actually reach the optimal risk, okay? We already derived this yesterday together, remember, right? That's okay. Now, the point is, in this case, what would happen to the expectation on the rho of the real risk? So that's a question I did not address actually yesterday. So turns out that for now, I will remove this assumption later, but for now, if you want to do this, okay, what happens is that instead of considering the risk exactly at the optimal parameter theta star, you're going to sample around theta star with the small perturbations. Obviously, if the risk moves a lot, a small perturbation will induce large discrepancy with the risk at the exact minimizer R of theta star. So I said for now, just to keep things simple, assume that we have a risk function that does not move too much. Say it's Lipschitz. So if the loss is Lipschitz, then you just take expectation, the risk is Lipschitz, okay? And in this case, if you sample, okay, in the small ball with radius epsilon around theta star, then the risk that you have will be actually the same risk than theta star, R star, plus at most the radius of the ball times the Lipschitz constant, okay? So it's a purely ad hoc assumption for now, and I will remove this in a few minutes, but for now, we just assume this, we have Lipschitz loss. And then you end up with a bound that's becoming more and more explicit, right? Okay, we still have a few things to fix in this bound, but essentially, we have now the R star in the right-hand side, and we have additional terms. We have the infimum in epsilon, but it's fine now, okay, because once again, I can use any rho I want in the right-hand side. So even though I decided to use this uniform distribution on the ball centered around theta star, I can at least also give me a degree of freedom on the epsilon. I can optimize the bound in epsilon. Okay. So I can do it. Let's do it. The point is actually, if you look at the function in epsilon, it's epsilon plus d log over c over epsilon over lambda. It's not super complicated function. You can just differentiate it. You get one critical point. It turns out to be the exact minimal, and it's reached for epsilon equal to d over lambda. Now you have this bound. Okay. Curiously, actually, in a review about that, I also got sometimes a comment that the function epsilon plus log of c over epsilon over lambda could not be exactly minimized, and that this was approximate. So I would feel very safe if you could check the derivation, but I think it's quite, it is exact actually. But anyway, so that's what you get. And finally, so I did not exactly optimize in lambda because in this case, it turns out it's just a little more, little less explicit. But if you take lambda of the order of square root of n over d, then you have actually the proof that the Gibbs estimator in expectation for large enough sample size will actually do as well as the optimal predictor in the class. And the rate is quite explicit. And sorry, I wrote this big O notation just out of laziness. I didn't want to write the exact constant, but when you see the second equation in the slide, you see clearly that actually we could have explicit constants here. There would be just, if you want to get tighter constant, you will have a small reminder terms extra. So just to simplify things, I just give the order of magnitude of the bound. So it's square root of the dimension over n, okay? Which is a little expected because it's the kind of rates we got in the empirical bounds yesterday. It clear so far? Okay. So I want to summarize this example because at some point I did something unnecessary. I reintroduced this Lipschitz assumption and it's not necessary actually. So I want to explain how to remove this one. And so first we proved the oracle version of Catoni's PAC-Bayes bound. And then I fixed uniform prior and uniform posterior. And what I used from the fact that they were uniform is only the fact that I had an explicit formula for KL and I was lazy to derive another one. And also, I use the fact that if I sample from the perturbed version of, like the rho, which is a perturbation around theta star, then I still have a risk that is close to the risk of theta star. I can maybe reverse my point of view, actually. A way to reverse my point of view is to assume, actually, that, or to change maybe, like, sorry, the rho, and instead of saying I absolutely want to sample from a ball, to sample from any posterior, as long as this posterior will satisfy this condition, that the risk will remain smaller than the optimal plus delta. Okay, so now finally we can visualize things, okay? You have a prior, so like in this drawing, actually the prior is uniform, but it could be anything. On the x-axis, you have theta. On the y-axis, you have the risk, okay? And then you have the risk function, and you see that the risk function reaches a minimum at a point here that I did not highlight, it's theta star. And then I want to choose a posterior that will not give mass for thetas whose excess risk is larger than delta. Okay, so it's exactly the zone here I highlighted in red. Okay. And of course, in this drawing, it turns out to be an interval which would match a ball in dimension D, but it might be more complicated. Okay, if the function has many local minima, you might have actually disjoint support for rho. Anyway, let's just take this rho. And this rho makes life super easy, right? Because in this case, you see that in Catoni's oracle bound, you can replace the expectation where theta is sampled from this rho, that is pi delta. It's upper bounded by definition. It's the very definition of this rho. It's upper bounded by the best risk plus delta. And then what appears here in this term, and that's, sorry, like if it's, I'm doing a lot of derivation, but I really wanted to make this term here appear explicitly. If you take this more general version, actually, instead of just a ball, but something that would adapt to the shape of the risk. Okay, so really, it's not only just changing the point of view, it's really something that is actually more clever, because in the first case, you want to impose your Euclidean ball. And in some sense, this is why I had to include the Lipschitz assumption, because you have to assume that the risk matches the geometry induced by your Euclidean ball, so that it is Lipschitz. Here, I did not impose any assumption on the shape of rho, okay? The shape of rho is really given by adapting to the shape of the risk function, okay? And the natural complexity term now that you have is the log of 1 over the probability under theta of the set of thetas such that the risk is smaller than r star plus delta. And that's actually very important quantity from a theoretical point of view. It's very central, actually, in all the theory of Bayesian statistics beyond PAC-Bayes. It tells you, in some sense, that what will guide the rate of convergence. So you have a practical procedure. You use PAC-Bayes, you use Gibbs estimator, you want to use it to train your model, whether it's a neural network, support vector machines, whatever, etc. Here, you have a set in red. That is the set of parameters that are maybe not completely optimal, but almost optimal. What is the probability of this set under pi is exactly what will drive your rate of convergence. In a lower bound, not in an upper bound, in the sense that if this set is too small under pi, then your rate will be bad because the 1 over this quantity will be large, okay? But if this set is large, then actually the bond will be good. You could anticipate this, okay, right? If pi is already equal to rho here, then you know that even your prior only gives mass to the best parameter. That's, of course, cheating, but that would lead to a good bound. In this case, you have something a little less optimistic, a little more realistic on the other hand, but this is exactly the quantity that drives the rate of convergence. And essentially now, I will switch the point of view before, actually, with the uniform distribution on Euclidean balls, we proved that the log of 1 over this probability was essentially equal to dimension over times the log of the radius of the balls. But now let me switch the point of view. If there is, so I don't assume anymore I have Euclidean balls, I might not have such an inequality, but if there is such an inequality, I will be happy. Okay? And essentially, that motivates the introduction of a definition, which is not exactly the same definition as the prior mass condition used in Bayesian statistics, but it's very close. And essentially, it's the following. So, is the prior probability of the event risk smaller, like almost optimal, delta optimal? Is it not too small? And if I can control the log of 1 over this probability by some d times log of some c over delta, then actually I will have exactly the same rate. Okay, and then you can just do the same optimization and you have the same rate of convergence. I want to insist on the fact that here we change the point of view and it's a more general result in the sense that you might have a situation where the optimal posterior is not like the posterior, like that's just on the delta optimal parameters, will no longer be a ball, but you could still get such constants. So in some sense, this kind of condition was checked by researchers in Bayesian statistics, in asymptotic Bayesian statistics, especially in Bayesian non-parametrics. So they have many of examples where this situation is satisfied. Essentially, any d-dimensional model with very minimal assumption on the likelihood, etc., logistic regression, whatever you want, you will always have such a condition. And the capital D here, the D here, will actually match more or less the dimension of the model. So it means that if you use PAC-Bayes on these models, you will recover this boundary square root of D over N. Now, one of the reasons why I wanted to discuss this is that yesterday, for neural networks, I mentioned, okay, the dimension, the real dimension is super large. And if you take square root of the real dimension over N, you will not get good bonds. What's interesting with this assumption here, the prior mass condition, is that it might be satisfied with D here that is much smaller than the actual dimension of the parameter space. Essentially, the minimum is super flat. If in some direction, the parameter absolutely don't matter, then you can take almost an infinite variance in these directions. And what it tells you is that when you move delta, the corresponding the corresponding direction, you will always remain in this set actually. So if you have a minimum that is flat in some directions, then the dimension D here in the assumption will decrease. So this explains from the theoretical point of view why the bounds could be good if you have a flat minimum. Now, yesterday, when I said these bounds work numerically on neural networks, but it doesn't explain why they work, what I meant is that on examples, people trained neural network by using these bounds, they found that the minimum was flat enough for the bound to be tight, but we cannot prove in advance that you will always have here the D that is actually smaller than the actual dimension. It's something empirical. So in some sense, if you use your PAC-Bayes bound in a program where you know that D is actually smaller than the dimension of the parameter space, you know it will work very well. But this is something that for most problems related to neural network, we cannot prove, actually. So, okay, so that's it for now for the just the introduction on excess risk bound. Maybe I will just cover, actually, before taking questions, I will just cover the question of fast rates. And I hope it will be interesting to you. At least it's something that is useful far beyond PAC-Bayes bonds. It's something really used for many algorithms related to PAC bonds, actually. As a motivation, I want to come back to these results that I explained yesterday. So if you have that's Tolchikin and Seldin's bond. And remember, this one is able to take advantage of the situation where you are in a realizable, I don't know how to pronounce this correctly, in a perfect zero risk setting. So actually, if the risk is, okay, the empirical risk is zero, then the bound, the PAC-Bayes bond that was in square root of KL over N becomes, remember, in KL over N. So here, in this case, the bond that we derived before in square root of D over N seems pessimistic. We would expect actually something in D over N. And it's feasible by using assumptions that are not specific to PAC-Bayes, but I still would like to review them. So I will give example. And the point is, and that's something here again that is not, I think, known well enough, is that people know that actually, okay, if the risk, if the optimal risk is zero, you can derive fast rates. But actually, it is far more general than this. And I want to show you a few examples. And some situations are really, really practical, actually. So first, I would say more general occurrence of such a situation was in classification with the 0-1 loss. So it might not be the most practical, but it's still a very intuitive, actually, example. So I want to explain it. When you start your classification 101 class in middle school, then you learn about the regression function eta, which is the conditional probability, the probability that y is in the positive class, okay, given x. And then you learn that the optimal classifier for the 0-1 loss is the so-called Bayes classifier, which unfortunately is not related to the Bayes in PAC-Bayes. I mean, but anyway. And say like, okay, if this probability is larger than 1/2, you predict 1. If it's smaller than 1/2, you predict 0. Okay. Actually, there's an assumption, so it's known as a Mammon and Sibakov margin assumption, that says that, okay, by the way, say if the risk is 0, you can get rid of the square root. If the risk is 0, it means that actually the function eta can only be equal to 0 or 1, right? In this case, you have perfect classification. But actually, Mammon and Sibakov proved that it's a much more general, a much more general assumption can lead to the same result. You just have to prevent your function eta to come arbitrarily close to 1/2. As long as there is a threshold tau here, positive, okay, such that the eta cannot get close to 1/2, smaller, like the distance to 1/2 cannot be smaller than tau, then actually you can prove a fast rate. So I mentioned here the paper by Mammon and Sibakov. Yes. Yeah, it's not, yes. It's written, actually, if theta star such that f star is equal to f theta star here. So that's, but anyway, that's still something nice in the sense that they have rates in 1/n and not in d over n in this case. So illustration, okay. What I meant, so x this time is not theta on the x-axis, it's x. On the y-axis, you have the regression function, then you have the values 0 and 1. Of course, the regression function is blue is between 0 and 1. So in the noiseless classification case, it would actually always be equal to 1 or equal to 0. But actually, it can even go within the interval 0, 1, as long as it doesn't enter this forbidden area, interval of length 2 tau around 1/2. Okay, Another setting, and probably more related to practical stuff you might be doing actually, is I wrote this between brackets, actually strongly convex and Lipschitz laws, because it's actually a little more general than that. But so just to shorten, just on this slide, actually, I will write g of theta for the loss of y and f theta of x. Okay, so I hide the dependence in x and y. And if you take the definition of Lipschitz and definition of strong convexity, and you apply it to G, you will have something like that, where delta is a metric. Okay. The point is that actually, as long as you can find such, as long as you can prove such inequalities for any function delta that might also depend on x and y, but I hide it so that it's not, I hid it, sorry, so that it's not unreadable. So as long as you can find a function delta so that you have these inequalities, then actually things will also be nice in the sense that like you have papers also like about 20 years ago, Bartlett et al., this one, like where actually they proved also fast rates under this assumption. So in this, like delta might not be exactly a metric. It might be a semi-metric or actually anything positive that depends on theta and theta star, and you will get derive the fast rate of convergence actually. I don't want to prove why, but what I wanted to explain, I will try to give an intuition. You see, the intuition will be like kind of approximate, very approximate. So you might shout out of anger. But before that, I just wanted to explain actually a kind of central assumption or in fast rates, and saying that if you look at both papers, the magic is not that they introduce an assumption and prove a fast rate. The magic is that they introduce an assumption, prove that it leads to an intermediate condition, which leads to fast rate. So actually, the end of the proof would be the same in both papers. And this condition is a Bernstein condition, which there is a more general version I will give later, but for now, I will just write it in this way. So actually, the expectation, right, it's a little more complicated. That's why I preferred to give the more like intuitive version in the beginning. But essentially, it says that you take the expectation of the loss function minus the optimal loss squared. And this should remain smaller than a constant times the same expectation without the square. And it turns out that by definition, the same expectation without the square, well, the expectation of the loss is the risk of theta, and the expectation of the loss of theta star is the risk of the optimal risk of R star. So you might have good intuition on it, and then in this case, you might say, yes, why did not you give this assumption first? I did not, so I prefer to give this as a kind of intermediate result, and now we will dig on this assumption a little. But the point is that in both cases, either in a Mammon and Sibakov paper or Bartlett et al. Paper, what they do actually, what is hidden somewhere, is that actually they prove that their condition leads to this Bernstein condition, which later leads to fast rate actually. And there are more conditions, so I will discuss a little more later. But for now, let me just give an intuition. And once again, don't shout because I know it's really not rigorous, but it's just like to give a kind of okay. You know how to compute the variance of a sum. It's the sum of the variances if the variables are independent, which they are here. So you get this, okay? So the expectation of the empirical risk minus the true risk squared is in 1 over S squared times the sum of this variance of the loss, which I can call like V of theta. Essentially, unless you are in the perfect classification case and theta is the optimal, otherwise it's a constant, okay? Then you use Jensen inequality. Expectation of the absolute value is smaller than the square root of the expectation of the square. And then you get that this is smaller than this variance over n. Make sense? Okay. So what it means, and once again, it's very, the proof actually is just making this a little more formal, but imagine this, that you stop thinking of the left-hand side as an expectation. You just think of a specific event in the before integration in the expectation. What you have is that if you have two parameters, theta and theta star, that have the same empirical risk, it doesn't say that the risk will be the same. All you have actually is that the risk will, like the difference between the risk will be in square root of variance over n. So of course, the difference between the risk cannot be huge. But you see, because like the first derivations are equality and the rest is not, it's quite tight actually, you cannot really hope to say more. if two parameters have the same risk in general, all you can say is that their risk might differ by 1 over square root of n, roughly. Okay, no hope to do more. Now, the thing is, if instead of comparing their risk, you compare their relative risk, that is, you compare the risk, empirical risk, like the distance between the empirical risk of theta and the empirical risk of theta star, okay? So I computed the variance of this quantity, the expectation of the differences of the empirical risk to the expectation, actually. Here again, it's a variance, and here again, a variance with many terms that I wanted to write completely, but anyway, it's just a variance of the sum, which is a sum of the variance because everything is independent. And the variance of something, so it is the expectation of this something minus its expectation squared, but it's also smaller than the expectation of the something squared. So the variance here of the difference of the losses between theta and theta star is upper bounded by the expectation of simply this L of loss minus the loss of theta star squared. I removed the expectation, okay? Variance of x is expectation of x squared minus expectation of x squared, and I just removed the minus to make things less tight. But the Bernstein assumption tells you that this is smaller than k over n for some constant k times the, the risk of theta minus r star. So that's just the statement of Bernstein assumption here. Expectation of the square of the difference of the loss is smaller than k times risk minus best risk. So just using Bernstein condition, I have this. And now, if you think, once again, in wrong terms, that is, you do a little whatever you want with what's inside the first expectation, but what you have is that if theta and theta star have the same empirical risk, then the real risk of theta minus the risk of theta star will be smaller than the bound we found. But this bound actually is in k over n times r of theta minus r star. So instead, this time of upper bounding this quantity by 1 and taking a square root, I can just cancel r minus r star on both sides of the inequality, and I get that the risk of theta minus the risk of r star is smaller than k over n. Make sense? So obviously it's completely wrong as a proof, but if instead of working with expectation, we work with large probability, then you will essentially derive PAC bond or a PAC-Bayes bond, and I just wanted to state it. So assume you are in a situation where you have Bernstein inequality. And once again, don't think in terms of Bernstein conditions, I think in terms of I am in a classification with small noise, or I am working with a Lipschitz and convex loss function, etc., etc. Then in this case, you have this PAC-Bayes inequality. So on the left-hand side, you have the difference between the real risk of your Gibbs procedure and the optimal risk. And on the right-hand side, you have also actually the same thing, but for some theta, and then you have the KL of rho and pi over n. Exactly as in the previous oracle bound, left-hand side, it's fixed. We use the Bernstein, the Gibbs classifier, actually. So now we have fixed learning procedure. But on the right-hand side, you have rho, any you want. It's an infimum, so you just play. And actually, you could reuse exactly the same trick. Okay, you could decide, I can upper bound the expectation on the rho of r minus r star by delta, make an assumption against the prior about the prior mass, and here actually immediately you would get a rate in well, you still have a log term, but apart from that, instead of square root of d over n, you have the d over n. Does it make sense? Yes. Okay. So first, I insist if you look at the papers by Sibakov and Mammon, or Bartlett and Jordan, McAuliffe, and they were like sequel by Bartlett and Mendelssohn, etc. They don't do it with Bayesian methods. These kind of things can also be used with empirical risk minimization. And then in this case, you don't have a prior mass condition, but you end up using Rademacher complexity, Vapnik dimension, or whatever tools you want. But the same technique would work, actually. So Bernstein condition is not only for PAC-Bayes, I insist on it. It's a general condition that would allow to derive fast rates. On the other hand, the thing I also want to insist on, because it was really like missing from the literature, is that PAC-Bayes bond is not stuck into the square root of d over n regime, and actually you can derive PAC-Bayes bond for fast rates, actually. So I just want to come back 1 minute on this condition, just to derive, okay, at least to show you why it's not always easy to check, and why actually it's nice that we have a Bartlett and Jordan result, or Mammon and Sibakov result, because very often people think it's easy to check this condition. Okay, the expectation of x squared is the expectation of x times x. That I agree, and we are in a bounded loss setting. Maybe you forgot, but yesterday at the beginning of my class, I said that until today, we will be in the bounded loss setting. So of course, see the second line here in the derivation, the difference between the loss of theta and the loss of theta star. Both of the losses were in the interval 0, 1, so this is smaller than 1. So that's fine. I can upper bound one of the terms by 1, and the other one remains. But the problem is that what you have when you bound x squared by x times x is actually you bound x squared by absolute value of x times absolute value of x. So then you have expectation of the absolute value of loss of theta minus the loss of theta star, which unfortunately, because you know that Jensen's inequality is never in the way you want, unfortunately, you cannot use to upper bound this by the difference of the risks. Okay? So it seems easy. And the first time I saw Bernstein condition, I say, oh, but I think I have a proof, actually, and super clever. And then after 2 lines, you say, oh, okay, wait. And everyone probably does the same at some point. There is a difficulty. Of course, it might be that, by the way, that the left-hand side is actually smaller than the right-hand side, but this would be very specific setting. For example, if you assume that there exists somewhere, like the best parameter theta star, is not only best in average, but it's best for any pair of data. Which is super realistic in general, but anyway, assume that it is the best for any pair of data, then actually the absolute value on the left-hand side is not an absolute value because the quantity is positive always, and thus actually you have the inequality, and thus Bernstein inequality is satisfied. So it's a condition that is of course super restrictive, but that would allow to unlock this very simple proof. But not that, still, if you assume that there is a parameter that has perfect risk, for example, it makes 0 error, then it's the thing that usually people use to get fast rates, then actually it's still less general than the above, okay? If you have a parameter that has a 0 risk, it is indeed uniformly better than the other parameters. So actually, I end up with a little more involved like representation of the conditions. Everything that you would find in most papers on PAC-Bayes is the R to get fast rate is the R star equals 0 condition. Actually, Mammon and Sibakov and Bartlett and Jordan also allow to derive the same fast rates, but everything goes through the Bernstein condition actually. Note, you can check, it's quite direct actually, that the R star equal to 0 implies Mammon and Sibakov condition. Funnily, there is no direct relation between just the uniformly best theta star and the Mammon and Sibakov. It's not that you might have a uniformly best that still goes arbitrarily close to 1/2. It's a made-up example, but it's still feasible actually. If you want to go further, and if you like arrows with diagrams with a lot of arrows, you can have a look at this one. Okay, when you look at this, maybe you don't want to read the paper, but actually you should. It's really an amazing paper. By Van Herven, Grunwald, Mehta, Reed, and Williamson. So Grunwald also, I did not cite his papers yesterday because they're more on the theoretical side than on the applied side of PAC-Bayes, but he's a specialist of MDL, minimum description length, and PAC-Bayes and information bounds. Van Herven, I mentioned this tutorial yesterday, but he was his PhD student. And yes, they wrote this paper, which covers a lot. They list a lot of the assumptions used in various research papers, either, by the way, on batch learning or online learning, to derive either smaller regrets or fast rates. And then when the conditions, like the relations between these conditions were not known, they checked it. So you would end up with 15 conditions, a nice graph. It's a lot of proof. It's a lot of work to read. But if you need information or, like my condition lead to fast rates, then actually you can get this information from this paper. So it's incredibly useful. So I really recommend it. I just want to mention practical examples. I will not do complete derivations in these examples, but still, I want to check if you do something as simple, and I recommend, I mean, if you're interested in PAC-Bayes, otherwise I know that probably Saturday you're going to the aquarium, but if you don't like fishes and if you like this, it's good as an exercise to compute the bounds on simple examples. If you want to do linear regression with the tools I gave you, honestly, it's a little annoying because we have bounded loss. Linear regression with bounded loss, it means that you have to assume that y, x, and theta are bounded, but it's still feasible. So you just can, impose restrictions. And then it's easy to check directly, actually, that the Bartlett et al. Condition is satisfied. Once you do it, you can derive for a linear regression in dimension d a bound in the square root of d over n, which up to the log term that remains actually is known to be minimax optimal. So essentially, you cannot hope to improve on this apart from the log term, which was done by Olivier Catoni in his book, and I will explain a little how it's done later. But I recommend you just to check, okay, that's the previous inequality. It's not very difficult, actually. You can really do things with actually the uniform bound, the uniform distribution on balls in this case. So that's an example where with the standard assumption on the loss, you can actually check all the prior mass condition and the Bernstein condition, etc. Just want to mention that it's not, that's something, okay, maybe I should have spent more time on it, but I just wanted to mention it, especially now that there are a lot of papers on information bounds and PAC-Bayes bound to prune neural networks. Pruning with PAC-Bayes bound or sparsity, etc., like things that that was done in simpler case like linear regression. So say that the dimension d is larger than n in the previous example. Okay, so obviously the bound is useless in this case, but on the other hand, it's known that you can do high dimensional regression under additional assumptions. For example, if the parameter is sparse. I assume that actually you hope that theta star might have a dimension, a number of non-zero components, d0, which is much smaller than d, actually. And in this case, only thing you have to do is to choose a prior distribution that might give enough mass to parameters with the entries exactly equal to 0. If you don't care about computational issues, of course you should, but at least just for 1 minute, if you don't care about computational issues, what you could do, okay, you could take a prior on each entry of theta, that is continuous, like uniform on AB because I want something bounded, but if you don't want bounded, you can just take Gaussian or whatever you want, but only with probability 1 minus p. And with probability p, it's exactly equal to 0. And if you use such a prior, at least for now, non-focusing on the algorithms, because this kind of prior is a little annoying from an algorithmic point of view, but anyway, then you can get a bound where the d over n from the previous slide is replaced by a d0 over n. Okay, so you have a sparsity bound, which means that if the parameter has less dimensions, okay, less non-zero entries than the ambient dimension of the space, you get the fast rate here. You don't have to pay for the whole dimension. First paper doing it with a PAC-Bayes bound was by Arnak Dalalian and Sasha Tsibakov, actually, and they did it in a slightly different setting. So actually the bound has restrictions on the design of, so that is on the distribution of the x's. But on the other hand, it works with unbounded, and actually the prior is neither uniform nor Gaussian. It's a student prior. For some reason, that actually leads to a better bound. We have a paper with Karim Lounisi on the same idea, but we really wanted exact sparsity, so we kept a prior that would give weights exactly to 0, and then use like kind of advanced MCMC algorithm. So it's a little heavy, but it works actually. Like if you're in dimension 10,000, you can still compute this, and you have performance that are, for example, like very competitive with Lasso or this kind of stuff. A few more examples, following more like the ideas of Dalalian and Tsibakov. Taiji Suzuki will give a lecture here next week, had a paper on tensor estimation and tensor completion. So Taiji was doing PAC-Bayes also at some point. You can do it for deep learning. So there were papers by Badreddin Sharif Abdelatif, he's a former PhD student of mine. Actually, he wrote a paper to prove that if you do variational inference on neural network, you would have the same kind of rates of convergence you have if you use other methods. But he used PAC-Bayes bounds to prove this, and there is a more recent paper, a little more general, by Stefan and Trabbs. And one of my PhD students also wanted to to work on the inverse problem coming from physics, actually, and prove that using PAC-Bayes bond, you can reconstruct quantum states from observations, from measurements, by using also the same kind of, exactly the same kind of technology. Okay, so that's, you have many, many applications of this. Essentially, it's now a really simple technology you can use to derive rates in many, many problems, but you have also algorithms that come with, at least if you think, obviously, your prior in the right terms. That is, some priors will give optimal rates of convergence, and then you might have to think a little to make this prior flexible enough so that you have an algorithm that would work with it. I just want to mention one last thing. Actually, what people call Bernstein condition is not what I called Bernstein condition so far, it's this. So they have a little more. They have not only the constant k, but also an exponent gamma. And what I called Bernstein condition so far was the special case where gamma is equal to 1. If gamma is equal to 0, well, something to the 0 is 1, and it just tells you that the difference of the risk squared is bounded by a constant, which is always the case in this class because I worked with bounded loss. So in some sense now, the Bernstein condition becomes something that is always true for gamma equal to 0. But it can be true for gamma larger than 0, and the larger gamma you have, the better rate you will get. And in the end, the rate is in 1 over 2 minus d over n times, to the 1 over 2 minus gamma. So see, if gamma is 1, then you have the rate in d over n. But if gamma is 0, so the less restrictive case, it's always satisfied, then actually you have the rate in the square root of d over n. You can have intermediate rates. And actually, it turns out that at least in terms of margin, Mammon and Sibakov also have an interpretation for this case, where you don't prevent the regression function to enter the forbidden area anymore, but it can only enter with small probability, actually. I just wanted to mention this. Of course, in practice, you don't know gamma in advance in many settings. I mean, you might know in the case where it's strongly convex and Lipschitz, but in general, you might not know. So we know algorithm that will recover the best gamma, like the best rate depending on gamma, even if you don't know gamma in advance. So adaptive algorithms, to my knowledge, we cannot do it with PAC-Bayes just with one single prior. We really have to do a model selection procedure where first you would do PAC-Bayes for each possible gamma, and then actually find a gamma by a model selection procedure. So to do it in a fully Bayesian way, I don't think actually it's possible. Okay, maybe we can take a 5-minute question break, and then I will cover the last topic, which is shorter actually. So if you had enough equations, be happy. It's almost the end. But, so I will not give anyone an opportunity to ask another question so that I have time to cover the last topic. Sorry, it's more derivations, but I really think that it's, well, they're not so much actually, and I really think that it's an important topic. Let's come back to the first PAC-Bayes bond, and not the one in expectation, the one we studied yesterday. So Catonis PAC-Bayes bond, and remember that the statement says that you fix first lambda and pi in Catonis bound, and then with large probability, the inequality will hold for any randomized estimator rho hat. And then actually we decided, okay, we will take rho hat equal to variational approximation if you want something practical in smaller models, or if you just care about the theory, you will consider the Gibbs posterior, etc., because it minimizes the right-hand side. And then what we did, naturally, we have now the tools, the bound in expectation, we have now the tools to derive rate of convergence, where we plugged this pi hat in red into the bound, but in the bound with the same lambda and pi. Okay, and it seems no one complained about it, so I assume that you all accepted it as quite natural, or you were sleeping, or both. But actually, the point is that it's not natural at all. One, why? When the first bound, you fix a prior because you have 2 for PAC-Bayes bounds, and then you get an estimator, and you're happy because you have a practical procedure. But then if you want to compute the error of this procedure, what tells you that you should compute the rate of convergence by using a different inequality, but the same prior? It's not at all obvious, actually, if you think, unless someone enforces you to do it and does it in the slides, okay? So actually, we should think of version 2, actually, of the PAC-Bayes bound in expectation, where we highlight that actually, so it's not, okay. You would not publish this one as a novelty with respect to this one in a conference paper, because the only thing I did is that I replaced small pi by big pi, so that's not a major contribution. But it highlights the fact that even if you build rho hat in red, like as a Gibbs estimator or anything from the first PAC-Bayes bound with a small pi, you can still use the PAC-Bayes bound in expectation with another pi. Why not, if it helps? Okay. And the first occurrence I found of this actually in the literature is in Catoni's book, the blue one from 2007. So he did that. And then actually the point is that then you realize that the minimum in pi, well, obviously just do a few simplifications, but actually the infimum on pi does, like, pi is not into the empirical risk, so it's only on the KL term, actually. So essentially, we now have a question, can we improve the bound by minimizing the second term, actually, in the last line of this slide, with respect to pi? And the point is, we can. And it's done explicitly, actually, in the beginning of the book of Olivier. Actually, he proved that if you consider the expectation of the KL between any randomized estimator and any pi, you can exactly split into two terms. So in some sense, like, you don't have exactly a Pythagorean inequality with KL, it's not a distance in general, but like, thanks to the expectation here, you have it. And what happens is that you have two terms. First, the KL between rho and its expectation. By the way, what do I mean by the expectation of a random probability distribution? I mean the distribution that has the expected density of rho as a density. Okay, so that's reminded here. And you have this term, and then you have a second term in the bound, and the second term in the bound is the KL between the expectation of rho and pi, and it's a perfectly useless term, because if you choose pi equal to the expectation of rho, which you can, then this term becomes exactly zero. Okay, so that's a very important thing, because it tells you immediately that if you want to minimize, once you have decided your rho hat, if you want to minimize the PAC bound in expectation in the right-hand side, then you can do it explicitly. Okay, and in the end, it appears that if you take, maybe you guess now, I mean, at least some of you who are more familiar than I am with the information theory, the expectation of KL of rho hat to its expectation. Well, let's call things U and V for 1 minute. You assume you have two random variables, U and V, distributed from a P, and they might be independent or not. So PU is the marginal of U, PV is the marginal of P, okay? Then if they are independent, P is the product, okay? It's just PU times PV. But if they're not independent, it's not the case. One way to quantify the independence between these two quantities is to compare P and PU and PV, okay? You can take the KL between these two distributions. And of course, if these two distributions are equal, we know that KL will be equal to 0. So you end up with this quantity that is non-negative, but will be 0 exactly when U and V are independent and positive otherwise. So this quantity is called the mutual information between U and V. Okay, and I absolutely hate this notation. I am a very angry person. I have a lot of hate, actually. You will see, but chat with me. I hate this notation, but on the other hand, you have to live with it. When you write expectation of U, you all are aware that it does not depend on U. It depends on the distribution of U. So you can replace expectation of U by expectation of V, even if V is different from U, because if they have the same distribution, it will still be the same. In the same way, this does not depend on U and V of UV. It depends on P and PU and PV. So be careful to this, because it will lead to weird notations later. Anyway, an important thing is that just a few line derivations, you get that you can rewrite the mutual information between U and V as the expectation of the KL of the conditional of V when you know U and the distribution of V. Okay, and then actually, if you take the previous line, it means that actually, if you replace PV by rho hat, PV given U by rho hat, so it's the conditional distribution of the parameter given the sample. You replace PU by actually the distribution of the sample. So U is the sample, and V is the sample, and U is the parameter theta. Then actually it tells you that the KL of the expectation of the KL between rho and its expectation is actually the mutual information between the parameter theta and the sample S. And here you see why I hate this notation. It does not depend on theta. I mean, I hate it not in general, but I hate it in the context of PAC-Bayes bond actually, because it will hide the fact that this depends on rho hat. Actually, it does not depend on theta. It depends on the distribution rho hat of theta. But anyway, we keep it in this way. So you can actually optimize the take-home message. You can optimize the prior in the PAC-Bayes bond of an expectation. And if you do so, you find a prior which is known, at least you have an explicit description. It's the expectation of your posterior. And then also, in this case, the KL is no longer the KL. It is the mutual information between the parameter and the sample under the distribution where the sample is sampled from the distribution of the sample, and then the parameter is sampled from rho hat, okay? And then, I mean, that's where it stops, by the way, in Catoni's book. So it stops there, and then actually later it draws consequences of this result. But derivations stop there. Turns out that you optimize the bound in lambda, and you get something which is extremely similar to a PAC-Bayes bound in expectation. Now the KL is replaced by this mutual information, which is better. Because we know it's better because it's actually like a KL, but you optimize the prior. And then I think, really, that was a part of Catoni's book that no one read, so that was forgotten for a few years. And in a completely different community, it was rediscovered years later under the mutual information bound. But like, it's not written as in the block in Catoni's book, but it's written until this part actually, so it was there. So these mutual information bound and PAC-Bayes bound, they are the, okay, two sides of the same love, or I don't know how to say it, like in a way, but it's the same thing, right? Essentially, you have the mutual information bound. You can always, if you don't know how to compute the right-hand side, and it's done very often actually in papers on information bounds, you can just replace I by a slightly looser bound by replacing I by the expectation of the KL between rho hat and pi for a pi that you can choose. Now you can choose the prior that you will plug in the bond also. On the other hand, if you take a PAC-Bayes bond and you wonder, is it tight? Can I make it tighter? Yes, you can make it tighter to the mutual information bound by optimizing the prior. So you can go from the left to the right and from the right to the left. Okay, that's so there's a strong connection between these two things. I want to tell you one thing that I did not actually write the proof of this here. I wrote it in the book. Essentially, if you use mutual information instead of PAC-Bayes, so you optimize a little the posterior. For example, this is how in his book, where actually it's in the previous book, 2004 book by Olivier. So he did not, at that time, he did not have the complete optimization with respect to the prior, but he still used things that are quite equivalent, and it kills the log term. So it's something quite known that essentially, if you have a dimension which comes from this prior mass condition or whatever, in some models, these information bounds will allow you to kill the log term actually. So finally, to get completely optimal rates of convergence. I just want to give another illustration, and that will be the last thing I will do, last technical thing I will do, but it's a little, okay, it's a funny derivation, so that's, okay, we just take the most simplest example, finite parameter set. So from previous experience, you trained 5 neural networks and you want to find the best one among these 5, or maybe you trained 10,000 and you want to find the best 10,000, okay. In this case, you can take as a randomized estimator a non-randomized estimator. That is the point mass at the ERM, and just like let's forget about everything about randomization. We just consider an estimator that is actually not randomized, and thus it's the empirical risk minimizer. Okay, and in this case, if you use the mutual information bound, it tells you that the real in expectation, the real risk is smaller than the true risk plus square root of the mutual information of this theta hat and the sample. Okay, by the way, always the same thing. You can switch the expectation, the infimum, blah, 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 and then the first term in the right-hand side becomes R star. So actually, you have a rate of convergence for the ERM in expectation, but this rate is given by the mutual information. And now how to compute this mutual information? And essentially, if you forget, you come back to this picture and say, okay, mutual information, I don't know, it looks complicated. Let's come back to the standard PAC-Bayes bound. It's easier. No problems, you can do it. You can do it, for example, with a uniform prior. If you immediately on the finite set, you have a uniform prior, your posterior is a Dirac mass. You can check immediately that actually the KL between the two is the log of the set of the parameters. So you will end up with this bound in square root of log m over 2n. It's known to be minimax optimal in the sense that there are configurations of the function f theta, there are distributions for x, etc., such that this rate cannot be improved. So if it cannot be improved in some situations, we should be done and we should be happy with this. The point is that a uniform result is not necessarily a good image of the truth, and it appears that in practice this is always loose actually. So we can see this with the mutual information actually. So point is, in this case, to compute exactly the mutual information between theta hat and the sample is not so easy. There's the trick actually is also the one from Catoni actually, where he said, okay, I'm going to reuse the trick that mutual information is upper bounded by KL between rho and pi, but I take a different pi because now I can take any one I want. And it took a pi which is already centered around the true parameter. Okay, so you see, it's the pi is proportional to x to the minus alpha delta, but delta of theta is actually a short for the risk minus the empirical risk. Look at the KL. You can just redo the derivation we did yesterday. Remember, because like we have the pi, you have an exp, so actually you take the log of an exponential, so you have explicit form for the mutual information. And just for short, actually, I'm going to put that the log of the sum, etc., is equal to some zeta or psi. Let me see, zeta. Okay. And then I have the following short, actually, for the mutual information bound. So the excess risk in expectation is bounded by a square root of alpha times the excess risk plus this psi that we'll have to come back to later over 2n. And now we all want to go for lunch, so I do the derivation. But like essentially, if you want to solve this inequality, you square it. You have the degree 2 polynomial. You can find the roots. You can find an upper bound for delta that is given by that. And then actually you wonder, how should I choose my alpha? Because I still have a flexibility on alpha. You don't know, maybe you should know now. It's the time to know what zeta is. But what's cool is that zeta is log of the sum of exponential of e to the minus alpha times the excess risk. Of course, if you don't want any improvement with respect to PAC-Bayes, you could come back to its log of sum of something that is bounded by 1, so you can still bound it by log m. But you can do better. Bandits, people will actually have a feeling of this probably. You know that if one of the arms is better than the others, things are easier, and you introduce always your delta of theta, your delta, sorry, that is actually the minimum between the reward of the best arm and the second arm. And if it's large, things are easier. Here, actually, the zeta log of 1 plus the sum of theta different from theta star of e of minus the risk, and then just saying like log of 1 plus x is smaller than x, you see that you have something which has a worst dependent in m. But on the other hand, if the difference between the best arm and the second arm is not too small, then the exponential might be super, super small, actually. And then you have to take alpha as large as you can. And check in the first bound, of course, you cannot take alpha equal to n squared because it would kill the bound. But actually, the best you can, not exactly the best, but approximate optimization, alpha is equal to square root of n, and you have this. Okay? So the the PAC-Bayes bound would tell you square root of log m over n. It's minimax optimal, so you cannot improve on it in the worst case, but you can improve on it almost all the time by this bound here. And this bound, of course, has the r star plus square root of log m over n, but there's a minimum between the log m and this e to the minus delta square root of 2n, actually. Delta is this constant that is given by the difference between the best arm and the second arm. So in the case where the best arm is really easy to find, the exponential term will really go close to 0. The first term in the square root will vanish, and you end up with something in 1 over 2n, actually. So Actually, when people derived, if you check at the proof in Tsibakov's paper and some of his students, of the optimality in this, of this bond in general, the worst case is actually exactly when theta star and another theta are so close that the difference between their risk is actually of the order 1 over square root of n. And in this case, when delta is of the order 1 over square root of n, you can see that here you don't have an improvement. But it is the almost situation. Almost all the time, apart from that, this problem is much, much, much easier, and you have a much faster rate. And interestingly, this really illustrates the power of this mutual information ID, which is quite powerful. It turns like a kind of, it still remove a kind of, I already told you, like in some sense, PAC-Bayes bond remove a little of the worst case bond from Vapnik's bond, but mutual information also remove the worst case, a little of the worst cases from the PAC-Bayes bond and can lead to some improvement. Actually, it's done by optimizing with respect to the prior. Okay, so I like this. So even if you don't, I'm happy that I did it because I like it anyway. So that's almost everything. I will just mention that there is, of course, a version of mutual information bound under Bernstein condition. I don't know where it was derived first. I know that Raginski has a lot of papers about it. At least, like there was recently a new tutorial on PAC-Bayes bond and mutual information bound by Hellstrom, Durizzi, Gage, and Raginski. They cover actually mostly the MI bonds. What did I want to say? Sorry, I have a blank. It's a good paper, I like it, but sorry, if you want to find this bond, for example, like something equivalent, it's stated in it. Okay, so if you're interested in these mutual information bounds, then you should read this document, actually. So okay, what happened is that Benjamin and some of the authors of this paper actually started to work on the tutorial of PAC-Bayes bond exactly when I started to work on mine, and we forgot to mention this to the other group. So at some point, when mine appeared on arXiv, they were a little annoyed, and then actually we discussed, and anyway, like as Maxim Raginski joined them and is a specialist of the MI bounds, they decided to reshape a little the thing so that it really gives focus on the information bound. So it's actually, as you see that maybe the PAC-Bayes is simpler, it's actually good probably to read them in order, actually. So this one appeared a few months ago on arXiv. Just want to mention very briefly topics not covered in this slide. Some of them correspond to questions that were asked yesterday. Some of them to questions that I asked myself. What happened when you have unbounded losses? Benjamin Gage and his PhD student Maxime Hadouche have a lot of work about that. There are other groups of authors. Borja Rodriguez Galvez also has like many nice papers about it. So there is a really recent literature on it that is quite interesting. Self-citation, of course, I like to self-cite. So, but I wanted to mention there are also works for non-IID and time series. So the bound is a little more loose, but we still can prove things actually. So if you want to discuss this, happy to do it. There were quite amazing work actually by Olivier Catoni, who switched from PAC-Bayes to robust estimation to study estimators that are absolutely not PAC-Bayes. But it's funny to realize that even to study non-PAC-Bayes estimators, you can use PAC-Bayes bond in the proof. First, by seeing the estimator as the center of a distribution, you perturb it a little, and then actually, so it gives a very powerful tool to study non-Bayesian estimators, and especially robust estimators. So there were like a really good series of papers by various authors on this. Charles, who is in the room somewhere, we have paper on meta learning, but there were many papers on meta learning, so that might be also a question that was asked to me actually. You have past tasks. From these past tasks, you learn some information. And you might want to reuse this information to build a better prior for the future tasks, actually. Of course, you can do it in practice. It's done. It seems to work in some settings. Does it work in theory? And in our paper, we prove that in some settings, it can really improve the rate of convergence. And the intuition is quite actually simple. You know this prior mass condition. We want a prior that gives mass to the interesting neighborhood. And actually, by learning from the previous task, you can. So there is, so I mentioned the paper we have with Charles and another one, but actually there are many, many other papers. Sorry that I cannot cite everything, but there is a more complete list in the arXiv document. A question that was recurring yesterday in the Slack channel, what can you replace your KL that we don't like by the Wasserstein that we all like? And the answer is, first, you can replace KL by many things, first on condition that you can prove it, okay? You cannot just take the bond, replace KL by anything. You have to prove that the bond still holds in this case. Of course, that's the first difficulty. In a paper with Benjamin, for example, at some point, we replaced the KL by the chi-squared. And if you think about it, if you just do it for the sake of doing it, it's really stupid because essentially in the rate you replace d over n by exponential of d over n. Not super good. The point is, there was a point in this paper, which is that we are able to prove this bond. They are easier to prove, and you can prove them for non-IID, unbounded data, etc. So that's good. Should you do it with Wasserstein? Many papers are doing it, and I agree that in many situations, it will probably help for the optimization of the bound. Now I have a question. I asked this question to some of the authors working, especially so now on the Wasserstein. So I mentioned a few, but there are many information bounds with Wasserstein or PAC-Bayes bound with Wasserstein. Discussing with the author, I asked them the question, like, using this Wasserstein KL bound, are you able, for example, in a model like I mentioned, for example, say linear regression, are you able to recover a rate in square root of d over n? And they told me, like, we don't know. So I think, I don't want to say that these bonds are not interesting. They have other advantages over PAC-Bayes bond, and certainly computational, and certainly they can deal with different kind of posteriors, etc. For me, I hope, and maybe you know, actually, maybe like some results appear recently or whatever, but like, I would like to understand when this bond might be tighter and when this bond will be less tight than PAC-Bayes bonds. And certainly they cannot always be tighter because PAC-Bayes bonds sometimes are minimax optimal, so it's not likely that they will always improve. But what are the conditions? Because if you replace KL by Wasserstein, you get something you can minimize easily, but it's 20 times larger than the one with KL, then there's no reason to be happy there, okay? So there is, I think, all these papers are so new, that it's a new topic, okay? But I really think that there is a question that is, in all these new papers, what is the improvement we get in the model we are familiar with? Open question, to my knowledge. And just wanted to brag that I know now how to include kanji in Beamer. But okay, thank you, thanks a lot.